So it's already 5 minutes, 6 at Indian time, and we plan to start at 6. So I would like to start now, and it's my pleasure to welcome you all at this international. Just a moment, because there is some power cut here. Sorry, just please wait for a moment. Because
Sure.
okay. So we are back, and we are already 5 minutes late, and there are several talks. So I would like to start. And before I speak a bit about the institute, the organizing institute, and our group, I would like to welcome you all on behalf of JP Institute of Information Technology, Noida, and also on behalf of the quantum information community in large. Then this department, we are organizing it from the Department of Physics and Material Science Engineering, JP Institute of Information Technology. And this department offers a master's program in physics, PhD in physics, but beyond that, we have a quantum information group primarily focused on quantum communication, or more specifically, quantum cryptography. However, we work on quantum algorithms, and our recent interest is photonic quantum computing. Glimpses of those things will appear when different people will interact from the group, and some of them will also give the talk. But the more interesting and the more exciting part of this conference is this is restricted to young scientists, and all the speakers are young, and all the session chairs are also young. And in this meeting, all the talks are very short, because recently we have observed that the concentration time of the people have been reduced. So very soon the topic will change. Each talk is about 12 minutes and 3 minutes for questionnaire. And sometime, as it is expected, that your questions will not be addressed within that short period of 3 minutes. So we'll expect that you ask those questions directly to the speaker, or you send us a mail, and I will forward those mails to the speaker. And you can also find out the speakers in LinkedIn and other places. The idea of this conference, as I mentioned, was to bring all the young scientists working on broad areas of quantum information as well as quantum optics together in one platform. Then when we planned, then we thought that there will be responses of the order of 150 or so, but we found out to our surprise that there are about 600 registrations. So a little more than 550 and little less than 600. And they are from 35 different countries. And we never expected registrations from small African countries like Congo. And there are speakers from Algeria, Morocco, and UK, US, Australia. Then we found that next challenge is to how to allow all these people to speak. So this was not desired, but we had to stop some people from speaking because the time was restricted and we had some limitations on that. We have to do this online meeting in such a way that people from Canada can also listen and people from Australia can also listen and people from China can be available in the same time. So some request for changing time has been incorporated and that lead to some changes in the program. However, I hope that everybody will be able to listen all the talks. And in case you find sometime that the meeting room is full because of its capacity, kindly join with the YouTube link. All the lectures will be live telecasted in the YouTube as well. And it's happening same at right now also. And apart from the speakers, the other audience who have submitted without abstract, they are already in large number in the YouTube. So you have a good number of audience and we hope we'll have a very good interaction. I once again apologize for small time for each talk and small time for interaction. But we hope that small time will use properly and we'll have a great discussion and have a great meeting for next 5 days. So as I mentioned that there are about 60 talks and about 600 participations. So there are 540 participation without talk. And each talk is of 12 minutes plus 3 minutes discussion. And in addition, these talks have been grouped into quantum optics, quantum sensing, quantum cryptography, quantum communication, etc. in different groups. And today's first sessions after introduction will be focused on quantum sensing. And Dr. Chiranjeev will be the first speaker. But before that, I would like to request Professor Ajay Ghatak, who was known to most of the Indian students, but there are other speakers from outside India. For them, I would like to introduce. He is a great teacher, and many of us learned quantum mechanics and optics from his books. And he was in Indian Institute of Technology for many years. And presently also he is a visiting professor. And he led National Academy of Science India as president. And he is much interested in quantum mechanics, optics, and popularization of science. So I would like to request Professor Khatak to say a few words and encourage all our young speakers and the young quantum scientists who are not speaking but participating in this conference. Over to Professor Khatak.
Thank you. Can you hear me, Professor Pathak? Can you hear me? Okay. So, thank you, Professor Pathak, for asking me to speak on this occasion. First of all, I would like to congratulate Professor Anirban Pathak for organizing this beautiful meeting. I have never participated in such a meeting, which is just focusing on the work done by our very young scientists who are the potential technologists, not only in our country, but abroad. So I'm really delighted about this unique concept of the meeting, and also extremely happy to know that so many people have registered, 600 people have registered from throughout the world. And this is because of the technology we have. And the quantum technology is also being emphasized in a very big way by our Prime Minister and the government. And we are hoping that we will also, Indian scientists and young scientists and older, not so young scientists will contribute in a big way in the development. So once again, I'm delighted to be here. I look forward to hearing some of you or most of you. I do not know whether, and as Professor Pathak mentioned that choosing the time zone becomes very difficult. It must be very late at night in Australia, very early in the morning in Canada or USA. And nevertheless, I think 6 p.m. is the right time for people in the Indian subcontinent and also in Europe and Australia. So with once again, I'm delighted and I would like to congratulate Professor Pathak for taking this initiative. And if this is successful, then there should be other meetings like this. And we are grateful for the technology. And I hope the technology takes us to greater heights in the near future. And I live long enough to see the effect of the technology and the deliberations of this meeting will certainly help in connecting scientists from different parts of the country and bring peace to this world. Thank you, Anirban. Congratulations. And I'm so happy that you are organizing this meeting. And my very best wishes for a very, very successful interaction between the young physicists and not so young physicists. Thank you.
Thank you, Professor Ghatak, and thanks everyone for joining this inauguration program and also in the meeting. So now it's my pleasure to introduce the session chair of the first session. So Dr. Sandeep Misra, who is a faculty colleague at JP Institute of Information Technology, and he's in our department, in the Department of Physics, and he works mostly on quantum cryptography. However, he has interest in quantum random number generator as well as in foundational issues related to quantum mechanics. But without elaborating much more, I would like to request Dr. Sandeep Misra to take over from here and chair the session.
Thank you, Professor Pathak. So I think the first session is quantum sensing, and since the schedule is widely tightly packed, so I think without wasting any time, let me introduce the first speaker, Chiranjeev Mukhopadhyay. Chiranjeev, are you here?
Yeah, I'm here. Can you hear me?
Yeah.
I am here. Am I audible?
Yeah. So yeah, you
Okay,
are
so
audible. So let me introduce him. Chiranjeev Mukhopadhyay. He has done his PhD from HRI, India, and then he is right now working in University Electronic Science and Technology of China. So and his topic of today's talk is modular quantum mini body sensors. So Chiranjeev, please share your screen.
Can you see the screen right now?
Yeah.
Okay. So can you see the entire slide?
Sure. Yeah, you can start.
Okay, so let's go forwards. By the way, thank you to Professor Mishra as well as Professor Pathak. And also, so as on a personal note, this is my first time seeing Professor Ghatak in person. We have all read his textbooks, but it's kind of inspiring as well as a bit intimidating, to be honest. Okay, so let's talk about quantum sensors. By the way, I mean, can you see the screen clearly, the entire screen?
Yeah, I am able to see the screen.
Yes.
Okay, perfect. So
Half of it.
Half of it? Yeah, I mean, that's what I also see. Okay.
Yeah, now it is okay.
Oh, okay. It's again like taking half of it. Okay, let's not waste further time. Just
now it is okay.
now it's okay, right?
Now it's okay.
Okay. So right now I am in Chengdu. So this is like a city in southwest of China. And the river that you see is the Jin River. So let's talk about the paper. The QR code that you are seeing is basically the archive version of the paper. It's accepted in PRL, but it's not published yet. So it's in the proof correction stage. So right now, I will first talk about quantum sensing. The core idea behind the main point of sensing anything is that you have an unknown parameter. Suppose that you want to measure the temperature of a room. And what do? You insert a thermometer in the room. And then from the thermometer readings, however amount of mercury rises or something, then you track it back to what the temperature should have been to cause that mercury rise. And then you find out the value of the parameter itself, like temperature. So any general sensing scheme follows the same protocol, that you have a probe which is prepared in a certain state, and then you let the probe interact with the parameter that you want to measure, so that the effect of the parameter is imprinted within the final state of the probe. You let the interaction go on for as long as you wish. And then finally, you measure on the system, you interrogate the system, you get some measurement statistics, which is wholly classical. And then from that measurement statistics, you want to construct an estimator. This is all classical statistics, nothing quantum about it. And then from the estimator themselves, you want to find out what value of the parameter should have given rise to that estimator. Okay, and we used an unbiased estimator, and for that peak should be go on being sharper and sharper as you have more and more measurement results. So where the quantum part comes in is that when you measure, you have a choice. You have a choice of measurement basis, which measurement basis that you are going to measure in. And depending upon the measurement basis, you have the statistics in a different way. Okay, so now I said that the estimator should behave more and more like the actual parameter value, so that after n number of rounds, the variance between the estimator and the actual probability distribution that you would get from the parameter value, if it was right, so they should coincide and the variance should go down and down. Okay, so after n rounds, the variance should go down as 1 by n. This is the central limit theorem. And the coefficient of 1 by n, so this term is called the fission information. This is, again, I mean, this concept is not very quantum. I mean, the fission information was known classically for statisticians for a long time. And the bound that you see, the variance of the estimator, which is greater than or equal to 1 by the number of rounds times the fission information, this is called the Cramer-Rao bound. And this is, again, a classical statistical bound. Now, where quantum mechanics enters into the picture is that the fission information, which depends on the measurement statistics probabilities, so this depends on whichever basis that you want to measure in. Okay. And the optimal basis that you are measuring in, that optimal, if you optimize over all possible basis, then this is called the quantum fission information. Okay, so our goal, in principle, if we can measure in all possible measurement basis, so first of all, I should make it clear that that's not possible in all of the scenarios, but in most of the scenarios, and especially including the ones that we are considering today, I mean, they will be accessible, at least we will assume so. So if you optimize over all possible measurement basis, then you maximize over the fission information because you want the variance low. So then you end up with the quantum fission information. Okay, so the formula for fission information is given and you can calculate it explicitly, which do not require any kind of optimization. I mean, there are like these geometric ways of putting it. So now let's look at what happens. We can view the problem in a way that you map whatever parameter that you want to estimate. So that parameter induces a phase shift in the system. Okay, and then you want to measure the phase shift with an interferometer. So you can map lots of problems to that, and then basically the entire problem turns down to how you measure an optical system, how you measure the phase shift of the system, and that's it. So now, if you have one single photon or one single qubit, then there is nothing very interesting going on. But if you take multiple photons, which are entangled, and then you allow the phase shift to take effect, if you, for example, if you start to prepare the system in a GIZ state and you allow the phase shift to take effect, then the phase shift introduces a phase shift in the entangled state. And when you calculate the fission information, this goes as the number of particles squared, which is different from the number of fission information being proportional to the number of particles in classical statistics, in classical systems. And because this is number of particles squared, as you go on increasing the number of particles, the estimation becomes more and more sharper. Because you remember that the variance of the parameter of the estimator is basically 1 by, some number of rounds times the fission information. So lower fission information is always helpful. So there is a quadratic advantage going on. So that's all good in theory. But in practice, what happens? So two things. One is that preparing this entangled state is enormously difficult because getting photons to interact with each other is difficult, number one. And number two, the state that I have written down, if you cut out one of the qubits, one of the photonic qubits, then what you are left off with is not very interesting. It's just a completely mixed state. So ideally, you should look for a system which has entanglement naturally. Creating entanglement should not be very difficult. So with that in mind, people talked about, instead of using photonic qubits, let's talk about many-body systems. We know that the ground states of many-body systems, as you go on at around t equal to 0, as you go on decreasing the temperature, the many-body systems, they have their own ground states being highly entangled. So the question now becomes, can we use that ground state entanglement to sense? So there is also another physical fact that at the ground state, at t equal to 0, everything is in the ground state. You have something called a quantum phase transition appearing in some many-body systems. And then what the quantum phase transition does is that at the transition point, if you look at kind of the Ginzburg-Landau kind of a picture point. Instead of having a single point where essentially the particle gathers around, you can have a multitude of different points, and therefore there is a phase transition going on here, where it goes from a well with one well to one potential with two wells. And at that point, the system is very fragile to say the parameter is like some parameter lambda equal to 6. Then if you change off the parameter from 6 to 6.01, then the system turns up into an entirely different state. And the difference between these two states, generally the states are close to orthogonal. The difference between these two states you can measure in a lab. Okay. So this is the phenomenon that we are going to be using. But now, I mean, there is a whole lot of literature in last 15, 20 years about using these kind of many-body systems for sensing. But now the problem is scalability. That these many-body systems, I mean, if you want to set up an Ising system, it's all very good to writing down a transverse Ising system in your piece of paper. But to actually implement it, you have to go through some hoops. You cannot implement just like a 30-spin Ising chain really easily. 15, 20, 25 in ion traps, modern ion traps, you can do. But then if you want to go to the real thermodynamic limit, this goes as, I mean, it's super difficult. Therefore, I mean, it is the same problem that is plaguing us with quantum computers as well. So having small quantum computers for demonstration purposes is really easy, but having large quantum computers is kind of difficult because, I mean, you cannot scale the thing up. So the best bet for us to scale everything up is to have a modular approach, that we have small chains, and then we just stitch them together with some interconnects. There are lots of technologies for interconnects coming up right now. And then we hope for the best, that we assume that these interconnects are perfectly okay. And then in that way, we string small chains together to have a larger chain. And that is the core idea of today's talk, that if you have a system which is modular, made up of small spin chains, and then we connect together these spin chains, is this still helpful for sensing? So the idea is that if we connect these small spin chains together, then some previous work, so there was one guy in Ukraine called Oleg Dereshko, and one. If you if you have this modular approach, then you can create in the transverse Ising field. We know that there is only one phase transition point, which is when the magnetic field is of the same order as the internal interactions. But if you have these modular kind of approaches, then there are lots of phase transitions happening because there are islands of disordered phases emerging within the ferromagnetic phase. And now, because there are islands emerging, there are more phase boundaries to play with. And previously, we saw that these phase boundaries are associated with better scaling of QFI, and ipso facto better quantum sensing. And this is exactly what we see, that exactly at this phase transition point, these phase transition points are newly created by modularities. And along these phase transition points, the fission information peaks. If you go to the bottom left plot, the fission information peaks. And when the fission information peaks, for both of these peaks, it goes as n square. I mean, essentially square of the number of total spins in the system. And whereas where it doesn't peak, it goes as n. The point is now, because you have lots of different phase boundaries to play with, then you can have this n square scaling almost everywhere, not just a single point in the phase space. Therefore, the tuning is easy, and you can create however number of phase transition points that you can create by just tweaking the number of the spins in each module, and that's it. Okay, so we saw this for transverse Ising chains, which is like a specific kind of phase transition, so the second order kind of phase transition, which has this Ginzburg-Landau kind of picture. But then we saw that the same idea can be carried over to topological systems as well. For topological systems, I'm just skipping slides here. Again, the same idea plays out, that if you have like a simple SSH system, which is the simplest possible topological system, then you have a phase transition between one where the winding number is 1 and one where the winding number is 0, which is topologically trivial and non-trivial. By two winding numbers, you can end up with 2, 4, 6, n number of winding numbers. I'm only showing the simplest example where you have 0 to 3, like 4 winding numbers. And for each winding number, you can have the phase boundaries. Now, instead of having one phase boundary, you can see lots of different phase boundaries here. And at each phase boundary, you can again recover the n squared scaling. I mean, we previously showed in one of our previous papers that at each phase boundary, the QFI should be going as n square. But now in the modular case, if you have the newly created phase boundaries, the QFI again goes as proportional to n square in each of the phase boundaries. Okay, so now and then we saw for 2D as well. So for 2D, it's I mean, for those of you who are familiar with condensed matter physics, it's really easy. So 2D the SSH is basically like 1D rice melee, and then you have the charge binding mechanism to make it 2D, and it has the similar kind of technical approach. And it also works for the 2D idea that even for 2D chains, you are creating new phase transition boundaries if you use modular chains instead of just uniform chains. Now, how useful is it? So we have new phase transition boundaries at which have n square scaling. But then, if instead of having a precise estimate of what the parameter value is, if we initially know that the parameter value is like within a certain range, instead of knowing exactly at 6 and optimizing our measurements over it, the parameter value we say that it's between 4 and 8, something, something. Then we have uh, the average of all possible measurement accuracies, and basically it goes as the average of official information. That's called the global estimation paradigm, where we are not sure initially about the parameter value which we take on. Okay, and for that scenario, what we see is, at least for the transversalizing case, we can have the same amount of precision. So if you look at the plots here, if we can have the same amount of precision for if you have a certain width to the system as the 4 times the size of uniform sensors, 3 times, 4 times the size of uniform sensors. So the modular sensor can be, number one, it's easier to make because it's modular. We just each modules together. Number two, it can allow us to have sensing precision, which is exactly the same as sensing precision for much, much longer uniform sensors. So instead of, that's one good advantage. And also, so if we may go over to the topological one, again, we see the same thing, that essentially we can reduce the advantage. I mean, we can have the same precision with half the size of the probe. So that's mostly it. I will stop now for questions.
Thanks, Chiranjeev. I think we can have one quick question, if anyone has.
Hi Chiranjeev, this is Abhishek.
Thanks,
So the question is, have you also tried to see the effect of noise here?
एक एक्स्ट्रा ले आना
Kind of systems?
और सर जुम्मा कल
Okay.
कल छुट्टी है ना
Could you,
Hello,
could you hear me?
If you could ask everyone to mute. If you could ask
someone.
everyone to mute.
Ajhar,
I can
please
hear
mute yourself.
Okay. Yeah, I can hear you. No, so there are 2 ways of looking at it. One is whether there is a thermal noise in the system that we go from T equal to 0 to like at high temperatures, where you will have like more excited states, like essentially at kind of qubit kind of system. So that can be looked at. And number 2 is that we can have noise in terms of the parameter value, other parameter values which are not changed. I mean, they being shifted a bit. I mean, these two are different. One is an open system problem. One is like a unitary evolution, but with different parameters. The second one, where we have the parameter values, other parameters values, which we do not want to measure, they're fluctuating a bit. I mean, and for the topological ones, it's also reasonably robust for like this other external noise kind of systems, because the topological indices, so these are basically global parameters. These are not local parameters where you have local noises and then everything goes all right. Okay. But for the full treatment, I haven't done the full treatment yet.
Because means not exactly the same thing. We were trying to do experiments on it, and previously I have done some experiments with the similar idea in solid state NMR kind of systems. And what we found is, it's you can consider just as a comment, and then we can discuss thoroughly. So because I'm interested in this, so what we found is the advantage starts failing.
So beyond a certain threshold noise. Hello, am I audible?
Is really what happens like now when you are talking about many body dynamics and many body systems. So implementing dynamical decoupling kind of like decoherence protecting ideas becomes very difficult. The reason being for most of these dynamical decoupling, I'm talking about the discrete dynamical decoupling, not the continuous ones. So they all require pi pulses, and pi pulses are not the pi pulses in practice. So, and finding out those corrections becomes difficult. So it is, I'm just saying that it is interesting to look into it in various ways. So if you have done those kind of studies, or if you plan to do, It will be very
So
interesting.
I can say two things. One is that with NMR, I mean, this is I'm just speaking off the top of my head because I'm not an experimentalist. But what I've heard from other experimentalists is that for implementing these kind of many body systems, the ion trap is really your best bet. I mean, you can do NMR, but to actually have like 25, 30, where the quantum advantage really kicks in, to go to that point, NMR would not be very ideal. But people
No, I am
routinely
not
do.
saying we have done only
Uh,
with NMR. There are now we are
Mhm.
trying to do with other systems as well. But in practice, this
uh,
is the problem of
uh,
effect of noise is has also been found in other kind of systems. I just said
sorry to interrupt
I
you. I
very much
think both
agree.
of you can discuss all those things later on because our second speaker is
okay,
waiting.
yeah, sorry. I
Oh, okay,
just
okay.
wanted to.
And
Okay, thank
I
you for
would
the question.
also
We can
like to
carry on.
request everyone except the speaker to keep their mic muted.
Okay, okay,
So let me thank Chiranjeev for this wonderful talk. So Chiranjeev, now you can unmute your unshare your screen.
okay, okay. Thank you. Thank you. And
Sec-
please, if anybody has any questions, please
so second speaker of this session is
just ask me on Gmail or whatever, LinkedIn. Thank you.
okay. Thank you. So second speaker of this session is Jingyan Yi from University of Electronic Science and Technology of China. So I think his topic is quantum enhanced sensing via Stark localization transition. So please share your screen, Jingyan, if you are
Okay.
okay.
Okay,
Yeah,
Dr. Sandy, you see my
I can.
screen?
Yeah, I can see your screen.
Okay. Okay, so let me share my slides. Okay.
Yeah.
So can I start or?
Sure. You can start.
Okay. So hello everyone, and I'm Xinjian He from the Institute of Fundamental Frontier Sciences of UESDC, and my topic is quantum enhanced sensitivity via Stark localization. And in today's talk, I will firstly give you some general concepts of quantum sensing, and then I will tell you about the Stark localization transition, and then how can we benefit from this type of criticality to achieve the quantum enhanced sensitivity. And then we will draw the conclusion. So firstly, in terms of the parameter estimation, it's basically the most fundamental applications to physics and engineering. So suppose that we will use some gravimetry to detect some rare minerals, and people are still using some kind of Rydberg atoms to detect the weak field, and people will also use these ME centers to detect the small chemical environment in cells and various the chemical environment in the single molecule proteins. And there is a very fundamental inequality in quantum sensing. It's called the Green-Brown inequality. It says that the standard deviation of the unknown parameter is inversely bounded by one over the square root of n times f, and here f is the Fisher information, and here is the definition of the Fisher information. And according to Dr. Chiranjeev's talk, we we already know that for quantum probe, the probability distribution is defined by the trace of this state and the POVM. And we know that if we're optimizing over all POVMs, we can achieve the quantum Fisher information, which is the quantum counterpart of the classical Fisher information. And there is also a closed form of the quantum Fisher information to be calculated for the pure states. And what's more interesting is that for classical probe, we can achieve the scaling of quantum Fisher information as L to the power 1 at most. And this is the so-called the standard quantum limit. And for quantum probe, if we use some say like highly entangled states like JZ states or null states, we can achieve the quantum Fisher information scales as scaling as L to the power beta. And here the beta can be boosted to 2 or even beyond. So now let me say a little bit about the quantum criticality. So suppose we have a parameterized Hamiltonian of H and the other parameter is the small h, and we just do the eigen decomposition, and we have this ground state, the GS of h, and then we look at some local observables of A, and then we just plot the expectation value of A as a function of H, and we may say some singular behavior of A around some specific point H critical. And so people have proved that near the critical point HC, we can achieve the scaling of quantum efficient information as L to beta, and here the value of beta can be greater than 1. So there are two open questions here. So one is that the most critical points HCs are finite. So sorry for the typo here. And can we achieve the weak field sensing, and can we achieve better precision? So our solution is like this. So suppose that we have a single particle tunneling with the rate J to its nearest neighbors, and we also have a linear gray field across the whole lattice. So so for the sake of the simplicity, we consider we're in the single particle subspace with critical point equal to 0 in the thermodynamic limit, and here we can rewrite our eigenstates of the total Hamiltonian H in a positional basis, and to visualize the behavior of the extended phase to the localized phase, we can firstly consider the value of H to be equal to 0, and then we can see that for both ground state and the main spectrum states, they are both they can both spread throughout the whole lattice. And if we add H a little bit larger to be equal to 0.1, we can see the both eigenstates can be localized around some specific sites. So here, from the panel left to the right, we can assume that there should be some kind of phase transition between these two behaviors. So let's plot the quantum efficient information as a function of the strength of the field H over J, and in panel A is the behavior of the ground state, and in panel B is the behavior of the middle spectrum states. And there are a few features we can see from these two figures. So firstly, we can see in the limits of the H close to 0, the quantum efficient information has a divergent behavior as the probe size L increases. And the next one is we can see there are several peak points of the quantum efficient information in panel B, which is can be the indicator of the phase transition point of such Hamiltonians, and the peak point H max can shift towards 0 as the probe size increases. And moreover, in the localized phase, the quantum efficient information has an algebraic gain behavior as H to the power minus alpha. And here the alpha takes different values for different energy levels. And then we just pick the maximum values of quantum efficient information and fit it as a function of the probe size L. And surprisingly, we see that the scaling factor, or the scaling x1 and beta, takes the value of approximately 6 or 4 for the ground states and for the mid spectrum states. And moreover, if we deviate away from a critical point to the localized phase, we can say the value of beta goes down from the 6 or 4 to 0 very quickly. And for the mid spectrum states, we can see the value of the beta still remains close to 4 in the extended phase. And reminding that we have this critical scaling behavior in the criticality, and we still have this algebraic behavior in the localized space. So here we assume that it might be of the second order type of the phase transition. So suppose we have a divergence of the length scale of xi scales as L h to the power minus nu, and here nu takes over speed of the divergence. And to verify this, we just do the so-called finite size scaling, and we just plot the Risk-scale quantum Fisher information as a function of this L to the 1 over nu times h minus h critical. And by checking the quality of the data class, we can see that it's indeed of the second order type of phase transition. So moreover, we know that in labs, what we have is not a quantum Fisher information. We can only get the probability distributions. So what we can get from the labs is only the classical counterparts of the quantum Fisher information, and so there rises a question that can we saturate the classical Fisher information to the quantum Fisher information? So here we have found a very simple positional basis to saturate the classical Fisher information. So here we just plot the classical Fisher information calculated by measuring this pi I of our ground state and the mean spectrum states for the two probe sizes L equal to 200 and 1000 together with this quantum counterpart, and we also check the scaling behavior of these two Fisher informations, and they are quite close. Yeah, and then in a more realistic scenario, we have established this behavioral quantum Fisher information for this Heisenberg chain together with this linear gradient field across the whole lattice. And following the same logic before, we have found that there is also a clear sign of the divergence and a clear sign of this decaying behavior of quantum Fisher information. And not too surprisingly, we can also achieve this scaling of L close to 4, which is also well beyond the Heisenberg limit. So what we have investigated here is that we just take a deep look into this effect of the non-linearity. So suppose that our gradient field is like I to the power gamma, and here gamma is the power of the non-linearity. So so after checking the scaling behavior of this quantum Fisher information below, we can see the scaling factor beta scales as okay, please.
Powering on.
Okay.
Spandan, do you have any question? I think the speaker can continue. I think you have 2 more minutes left. 2 more minutes.
Okay, so so the scaling factor for the single poly probe established before is like beta close to 2 gamma plus 4, but for the many body probe we have a larger speed of this scaling, says that 3.6.
Shantanu,
hello.
You can ask. Do you want to ask any?
Sir, I have a question.
Okay, please.
Hello. Yes, sir. Yes, sir. Hello.
Hello. Yeah. Please ask. Please ask.
Sir, how they will fit a mathematical term This is a non-linearity. How they will fit in mathematical form?
Sorry, could you repeat the question?
Sir, my question is that how they will fit a mathematical formulation or mathematical chart in nonlinear effect, in super Heisenberg sensitivity and finite scaling in optical measurement and many-body
Uh,
interactive problem. How they will fit in mathematical form? My question is that.
I'm not sure if I understand the question correctly, but here we have just established our Hamiltonian in this I to the power gamma, and here I is the set index, and gamma is the power of the non-linearity. And here we only check the how the scaling factor behaves as a function of this nonlinear power.
Yeah, speaker, you can continue. You have
Okay.
2 minutes left. Please conclude.
Okay, thank you. So here in the plot, we can see there is a clear intersection between these two lines, and we know that that after gamma equal to 2.5, we can get a better scalability of this quantum Fisher information for the many-body probe. And here goes the take-home message. So firstly, our start code is precise to measure weak gradient fields with strong super Heisenberg precision, say quantum Fisher information scales as L to 6 for single body probe with linear field and scales as L to the power 8 for the quadratic field. And from the finite size scaling, we have determined the critical points governing the scaling as well as the algebraic decaying behavior in thermodynamic limits. And for the single particle probe, the position measurement is the best one. Okay, so thank you everyone.
Let's thank the
Do you
speaker.
have
It
any
was very
questions?
nice talk. I think since we are going over time, so let's thank the speaker and move to the third speaker of this session.
Okay, thank you.
So third speaker of the session is M. Suman from Indian Institute of Technology, Tirupati, and his topic of the presentation is probing quantum phase transition via quantum speed limit. So Suman, are you here?
Yes, I'm
Yeah,
here. Can you hear
please
me?
share your screen. Yeah, I can
Sure.
hear you. Please share your screen and you can start your presentation.
Yeah. Oh, the last slide. So
So,
can
so
you
you
see?
have 12 minutes. Sorry to interrupt, but you have 12 minutes and then 3 minutes will be for discussion.
Sure. Can you see the slide?
Yes, it's visible.
Okay then. So I'm M. Suman, and today I'll be telling how to find the phase transition just by using the quantum speed limit. So before that, I'll explain what is quantum speed limit. So suppose consider we have some initial state psi naught of a system, and you evolve this initial state with respect to some Hamiltonian, and it will go to some final state psi of t. So the minimum time required for this kind of evolution is called as a quantum speed limit. And we have 3 bonds for this quantum speed limit. That is a empty bond, ML bond, and a ML star bond. So to calculate the empty bond, we take the variance of the Hamiltonian with respect to initial state. In case of the ML bond, we calculate the average of a Hamiltonian with respect to initial state, subtracting with the ground state energy of this Hamiltonian. In case of ML star bond, we subtract the maximum energy with average of the Hamiltonian. So this works for the orthogonal states only. What I mean is, here we consider that our initial state will surely go to the orthogonal state under this Hamiltonian. So what we define quantum speed limit as maximum of all the 3 bonds here. And we can see that this quantum speed limit is a function of 2 things. That's a Hamiltonian and an initial state. So let me explain what is a phase transition here. What's phase transition I am talking about. So here, consider a one-dimensional lattice. Let's say you have a lattice with some on-site potential, epsilon1, epsilon2, and so on. And consider the electron, one electron in this lattice. And this electron can jump to different lattice sites with some hopping strength J. So what we can think is, if this hopping strength is much greater than the on-site potential, then electron will be delocalized. It can move from one lattice point to another lattice point easily. But if on-site potential is greater than the hopping strength, then electron may not be able to hop to other site. It could be localized in some site. So what we can expect is at some point, like J equal to this hopping strength, there could be a phase transition from localized to delocalized state. And usually what we call this as a metal insulator phase transition. We see delocalized phase as a metal and a localized phase as an insulator. So the Hamiltonian for the earlier model which I explained can be given by this form. This is known as the Abraham model. So the first summation consists of two terms. The first term is a C dagger C. C dagger is a fermionic creation operator and C is an annihilation operator. So what the first term do is it destroys the electron at a site K and create the electron at next site. That's a K plus 1. Similarly, the second term destroy the electron at a K plus 1 and create at site K. So it has a hopping strength J, just like we explained in the previous slide. And we have an on-site potential in the second summation. That is, we have a cos of 2 pi alpha K. Here alpha is an irrational number. So we choose irrational number because it gives some kind of a pseudo-random potential. So this alpha, introduction of the alpha will give a pseudo-random. It won't be a periodic potential anymore. So delta is an incommensurate potential. That means delta is the strength of this pseudo-randomness. So suppose if we diagonalize this Hamiltonian and find the eigenstate of this Hamiltonian, what we observe is if delta is less than 2J, eigenstate will be the delocalized. But if delta is greater than 2J, we obtain the eigenstate to be localized. And we can see that there will be localization, delocalization, phase transition at exactly delta equal to 2J. If there is any question, then please ask.
You can continue.
Yeah, sure. So if I plot the eigenstate, that is in the x-axis, if I plot the lattice location, in this case, I took the 100 lattice points. In the y-axis, if I have a probability of finding the electron at a particular lattice set, the localized space, you can see that at around 52, the probability of finding the electron is 1. But in the delocalized space, you can see that the probability is distributed in all the lattice locations. So now I'll explain how to find this phase transition using our quantum speed limit. So first of all, we have the Hamiltonian here, and I'll set J to be constant, and that is equal to 1 for convenience and for the numerical calculations. First thing we have to do is we have to find the quantum speed limit of this Hamiltonian, which is a function of delta, and initial state, which is a delocalized state. So in this case, the delocalized state means the eigenstate of this Hamiltonian when delta equal to 0. So we take this Hamiltonian and the delocalized state, find the quantum speed limit and plot it with respect to this parameter delta. In this, I have denoted it as a delta f for convenience. So it's a decreasing function. Similarly, if we do the same thing, that is calculating quantum speed limit for this Hamiltonian, again with the parameter delta, but this time we take the initial state to be localized phase, localized state. So delta is like 1000. So eigenstate of the Hamiltonian when delta equal to 1000, 10,000 here. will give the quantum speed limit, and if we plot it, we will get an increasing function. So interestingly, we observed that whenever this 2 point intersect, this 2 point actually intersect at delta equal to 2. So that's what we can observe from this plot. And interestingly, this is also the phase transition point of this Hamiltonian. So in general, so what I'll conclude it, that is for incommensurate lattice potential, the phase transition occur at delta equal to 2J. And by following the protocol that I explained, that's using the quantum speed limit, we can actually capture the approximate phase transition. And future research may include detecting the mobility errors. So why I'm underlying the approximate phase transition is, we have checked this method for different Hamiltonian, and what we observe is it gives an approximate phase transition. It's not an exact, but it gives a quite very good approximation to the phase transition. And the result that I explained is published in PR. If somebody is interested, then they can look into it. Thank you.
Thank you, Suman, for such a nice talk. So I think
Sure.
we can have one or two quick questions.
Yes, sure.
Any question? Yeah, please ask.
Yeah.
So in slide 6,
Yeah, sure.
the state we are calculating is ground state, right?
Yeah, actually, it also works for all the eigenstate of the Hamiltonian. So it need not be the ground state.
Okay.
Yeah.
And why we have chosen 0 and 1000, these two values
Yeah.
only?
So actually, you can choose the values beyond 0 as well, but it has to be less than 2. And in the second case, you can choose any value, but it has to be greater than 2. But if you're choosing 0 and like very high values, you can also get the analytical calculation values of this. That's all.
Oh.
Yeah.
Yes, sir, thank you.
Welcome.
Let's thank the speaker. Very interesting talk. So
Sorry, I had one question. If I can
sure.
ask.
Sure.
Sorry. So nice talk, Suman. So regarding the question that was asked also, I just have a small question. So if you start, say the delta is very close to 2, but you're on the left side of the phase, right? Let's say you are in the localized phase and you are going towards the delocalized side.
Yeah.
Now, if you start very close to the critical point, there might be non-adiabatic effects, right? So
yeah.
So it so do you like it might not be always like this might not always work if you are very close to the critical point, right?
Yeah, you are
Because essentially
absolutely
this is
right.
like a spread of correlations that you're calculating, and then you're seeing this. So yeah.
Yeah, you are absolutely right. So what we observe is whenever we are very close to this critical point,
yeah,
this point actually, the intersection point actually deviates from 2, but when you are going away slowly, when you're going slowly away from delta equal to 2, it slowly come back at 2. So we see some deviation. That is true.
Yes.
Yeah.
So yeah, I think okay. Just wanted to clarify this. Thank you so much.
I think if there are some more questions, then that can be emailed to him, Suman.
Yeah, anybody can email.
Sure. So let's thank the speaker because our next speaker is waiting.
Yeah.
So Suman, please unshare your screen.
Sure. Thank you.
So fourth speaker of this session is Harsha Mariam Rezi from Indian Institute of Technology, Dharawad. So his topic is conditions for separability in multi-qubit systems with an accelerating qubits using a conditional entropy. So now you can share your screen. Yeah, it's visible.
Okay, thank
Yeah.
you. I am Harsha Ramraji, and the topic for today's presentation is non-separability in multi-qubit states with an accelerating subsystem. So first, let me give a brief
slightly
outline.
louder?
Sure, sir. Let me give a brief outline of the presentation. So first, we will see how a state transforms when one of its qubits is relativistically accelerated. then we introduce the ARQ conditional entropies, which is used to study the non-separability in these accelerated states. So then the conditions on non-separability for different n-qubit states are presented. The work presented here is like published in PRA. The details are given here. So first, let's consider a 2-qubit state shared between Alice and Bob. It is like we consider the state as in given in equation 1. So when Bob accelerates with his qubit with respect to Alice, who's in inertial frame, he sees a different space-time around him. And this accelerated Bob will from now on be called as Rob. So now Alice is in the inertial frame and Rob is in the non-inertial frame. So the inertial particles or qubits can be represented using like Minkowski coordinates, whereas like non-inertial qubits cannot be represented using these coordinates. So we use a different coordinates called the Rindler coordinates to represent these non-inertial particles. So because of Unruh effect, a vacuum state in the Minkowski coordinates transform as a two-mode squeezed vacuum state in the Rindler coordinates. And here, the squeezing parameter of the two-mode squeezed vacuum state will be related to the acceleration of this accelerated qubit. Similarly, excited state also transforms as a different like a two-mode squeezed vacuum state. So there are like two modes in this transform state, and these two modes corresponds to two different regions of the Rindler spacetime. Region 1, which is given in pink, and region 2, which is given in green. Here, the hyperbolas denote the trajectory of this accelerated particle. So we can see that the hyperbolas in like the pink region and like the green region are like causally disconnected, and a particle which is accelerating in region 1 cannot travel to region 2, or similarly a antiparticle which is accelerating in region 2 cannot travel to the region 1. So since these two are causally disconnected, when we write the final state of the inertial Alice and the non-inertial Rob, we have to trace out one of the regions of the space-time. So initially we had like a composite state of Alice and Bob as AB. Then it became Alice and Rob in region 1 and region 2. But now after tracing out, our final state of inertial Alice and non-inertial Rob will look as rho A R1, where we remove the subscript of 1. So, for example, if we have a generalized pure 2-qubit GHZ state shared between Alice and Bob, in inertial frame, it will look as given in equation 2. And when Bob is accelerating with respect to Alice, the state transforms as shown in equation 3. Now, since we have traced out one of the regions of this state, the end state is a mixed state, and to study the non-separability in this mixed states, we use entropy called Abrashkoval Q conditional entropy. This entropy is as can be calculated as given in equation 4, and it's suitable for mixed states. And the ARQ conditional entropy gives negative values if the state is separable, and it's positive when the state is it gives negative values when the state is non-separable, and it is positive when the state is separable. Now we have like this is the variation of ARQ conditional entropy for the generalized 2-qubit state when one of its qubit is or Bob is accelerating. Here, the x-axis and y-axis denote the state parameter in figure A, and like the acceleration lambda. So we have taken lambda is equal to tan HR. So when we vary from lambda is equal to 0 to 1, it will cover the entire range of R is far from 0 to infinity. And we can see that the ARQ conditional entropy is negative everywhere. That means the state is non-separable everywhere, and maximum non-separability is achieved for some particular state parameter values. So this maximum non-separability is achieved for Bell state 1 by root 2 0 0 plus 1 1, and we have plotted the ARQ conditional entropy for that state in figure B. We can see that with respect to acceleration, the state is more non-separable in the low acceleration region, and the state becomes lesser and lesser non-separable as acceleration increases, and it tends to separability in the infinite acceleration limit. We have done similar study for n-qubit pure states with one of its qubit in acceleration, and we have I have tabulated the results here. So since ARQ conditional entropy depends on the eigenvalues of the system and subsystem, it remains same for independent of n for n-qubit GHZ state when one of its qubit is accelerated. And for W state, it depends on n, and like for different n's, it is shown here. But for all pure states, if the state is already non-separable in the inertial frame, accelerating one of the qubits also keeps the state non-separable. It doesn't become separable anywhere, except in the it tends towards separability in the infinite acceleration limit. Now, we have done the same study for mixed states. So we consider the mixed state by adding a white noise to the maximally entangled state, which is like given in equation 5. P is the mixing parameter, and when this mixed state is shared between Alice and Bob is accelerating with respect to Alice, the transformed state of inertial Alice and like non-inertial Rob is as given in equation 6. So for this, again, we study the non-separability using ARQ conditional entropy. The variation of ARQ conditional entropy for the state as a function of the mixing parameter P and acceleration lambda is given in figure A. Here the blue region represents the non-separable states and the red region represents the separable states. So we can see that there is a clear separability, non-separability to separability transition which occurs for a different at different acceleration. So this plot is for like and we can see that like depending on the color of blue, the states are more non-separable at lower acceleration and lower mixing parameter. Then this plot is for the entropy parameter Q is equal to 2. We vary the entropy parameter and see that the transition curve saturates to a particular fixed curve as Q increases. That is shown in figure B. The fixed curve for this transition from non-separability to separability in the infinite like Q limit is given in C. Here again, like the blue region represents the non-separable states and the red region represents the separable states. So using this data, we can get a condition for separability or like condition for non-separability in this state. So the data we obtain is like curve fitted to an equation of the form P by A power x plus lambda power y is equal to 1, where P is like the mixing parameter of the state and lambda is the acceleration of the state. So for a GHZ 2-qubit GHZ state with one of its qubits, mixed GHZ state with one of its qubit in acceleration, this can be obtained as given in equation 7. So now we have obtained a condition for non-separability in terms of the mixing parameter and lambda. And we can also see that when both the qubits are in inertial frame, that is lambda is equal to 0, this condition reduces to P greater than 2 by 3, which is the necessary and sufficient condition for separability of 2-qubit mixed GHZ state. Now,
sorry to interrupt you. Sorry to interrupt. You have 2 more minutes.
Okay, sir. Now we have extended to this to n-qubit mixed multi-qubit states, and here on the left side is for like GHZ states and like right side is for W states. Here we have shown the non-separability to separability transition for n is equal to 3, 4, 5 GHZ qubit states and like n is equal to 3, 4, 5 W with 1 qubit in acceleration. The separability criteria obtained is like shown in the table. And now to see how well our separability criteria fares with other criteria, like we do a comparison with logarithmic negativity. Logarithmic negativity is like as defined in like equation 8, and we know that logarithmic negativity is 0 for separable states and it's greater than 0 for entangled states. Now this is a comparison of logarithmic negative non-separability to separability transition from ARQ conditional entropy and entanglement to separability transition from logarithmic negativity. This dash dotted curves are for ARQ conditional entropy and solid lines are for logarithmic negativity. So n is equal to 2 is denoted by black, violet is 3 and blue is 4. So we can see that for n is equal to 2, logarithmic negativity and ARQ conditional entropy kind of give a similar transition point, but we can see that as n increases, ARQ conditional entropy, which is dash dotted, gives a stricter condition on non-separability to separability transition. Here, the figure A is for n-qubit GHZ states and figure B is for n-qubit W states. So in both these states, we observe similar pattern, and we can say that ARQ conditional entropy is advantageous as we can obtain a stronger condition for non-separability. Now, to conclude my talk, we saw how non-separability varies in like pure and mixed states when one of its qubits is in acceleration. All the non-separable pure states in the inertial frame remain non-separable when one of its qubits were accelerated, and they had a higher non-separability in the lower acceleration, and it tends towards separability in the infinite acceleration limit. It was for pure states, it was independent of n for GHZ states, whereas it depended on n for W states. And for mixed states, we see that non-separability reduces as acceleration increases, similar to pure states, and the conditional entropy was minimum in low acceleration and low mixing, where it had a higher non-separability. And we also could obtain a separability criteria in terms of mixing parameter and the acceleration of the qubit. And we could see that the separability criteria obtained from ARQ conditional entropy had imposed strict conditions on non-separability than logarithmic negativity for n-qubit GHZ and mixed n-qubit GHZ and W states with one of its qubits under acceleration. Thank you.
Thank you, Harsha. I think there is one question in chat box by Ashish. So he want to ask that how does increase in acceleration lead to separability or reduction in entanglement?
It's
Ashish
when actually the accelerated state behaves like a squeezed vacuum state. There is something called as Unruh effect, and because of which the particle content of that an accelerating particle will be different from what it sees, will be different from what an inertial particle sees. So when you look at it from the inertial perspective, it will look as both are entangled, maximally entangled. But from the perspective of the accelerating particle, as it is moving farther away, the correlations reduce, and it feels like for the accelerating particle as if the entanglement is reducing. So it's about like perspective of which observer you are seeing. And since we have also traced out like two regions, like there are two regions, we have traced out one region when we consider the final state. So some correlation of that region with the inertial particle is also lost.
I hope this question has been answered. So I think I can take one more question if there is.
Sorry to interrupt here, but so in this case, by squeezing, we mean reduction in uncertainty. So does that in some way lead to an increase in the information? And is that related to how you're saying that by reduction of entanglement, mixing is also reduced? So that means information is the concept of information now between these two guys is increasing. Is that kind of, am I going in the right direction there, or am I missing the point?
No, actually, no, it's like information in like one region is reduced because we don't have access to one of the regions. So in the end, because of acceleration, the information between the two entangled states are reducing.
So I think let's now thank the speaker because our next speaker is already waiting. Fine. So thank you, Harsha.
Thank you.
Yeah.
Thank you so much.
Please unshare your screen. So next speaker of this session is Javed Naiko. He is from Adam Mickiewicz University, Poland, and the topic of his presentation is enhanced quantum sensing by capitalizing on the dynamical singularities. So Javed, please share
Yeah,
your
hi.
screen and you can start the presentation.
Yeah, is my screen visible?
Yeah, it's visible and your
Ah.
voice is also audible.
Okay, good. So let me start by thanking the organizers of this meeting and also allowing me to be part of it. I'll be talking about this work that was done in collaboration with Janek Kolodensky from University of Warsaw and Ravindra Chajlani, who is the faculty here at the Adam Mickiewicz University. The work is essentially about enhancing quantum sensors by capitalizing on dynamical singularities of the underlying Hamiltonian and non-hermitian dynamical generator. And I'm not able to. Okay. So let me start with a brief one-slide overview of quantum metrology. We heard earlier about quantum Fisher information. The general task of quantum parameter estimation or estimation theory in general is that you are given a state and this state interacts with some environment. And as a consequence of this interaction, some unknown parameters get encoded in this state. And your job is to estimate these unknown parameters. So at first, this task seems to be hopeless because the parameters are completely unknown to you, and you want to make measurements on this output state and to know something about these unknown parameters. But thankfully, there is this nice Cramera bound that tells you that no matter what measurement strategy you choose, you are never going to go beyond this bound that is given by the inverse of the Fisher information. In quantum setting, it is well known that the use of entangled states helps you to do better in the sense that if you use n probe states in separation, you're left with the standard quantum limit. However, if the same probe states are put in entanglement, then you get the inverse quadratic scaling, which is called a Heisenberg limit. However, there has been a change in paradigm where people have started looking at how the open system effectors, which arise from which lead to the non-hermitian dynamical generators, can be actually tamed to do some impressive quantum metrology. A typical setup consists of n bosonic modes in some optical cavity, and these modes have some loss and gain rates that can be modeled by their interactions with different types of reservoirs. And if there is some unknown parameter, for example, some epsilon parameter, which is encoded in the coupling strength between the two modes, and you want to estimate this unknown parameter, what you do is you let a probe field interact with these cavity modes and read the output field mode, and this output field mode is going to carry information about the parameter epsilon. For this general setup, the equation of motion is given by this equation 1, where you see this H in the bold is the dynamical generator, which often turns out to be a non-hermitian quantity. Let me take a digression and tell you how non-hermitian Hamiltonians work as better sensors compared to the Hermitian counterparts. If you have a Hermitian Hamiltonian H0 and you perturb it by some perturbation theta through a matrix H1, then you can expand the energies or the frequencies in the Taylor series given by 5, and this Taylor series is just in the integer powers of the perturbation. However, if this H0 turns out to be a non-Hermitian Hamiltonian, you still have this Taylor kind of series, but not in the integral powers, but in fractional powers, and this is called the Newton-Foiseau expansion. Now, if you restrict to the leading order terms, because theta is small, theta to the power 1 over n dominates theta. So in the simple case, for example, when n is equal to 2, okay, but n is the order of exceptional point. I should have been more precise in defining an exceptional point is a point where not only the eigenvalues of the Hamiltonian become identical, but so do the corresponding eigenvectors. So all the eigenvectors coalesce at these points, and so do the eigenvalues, and such points of degeneracies are called exceptional points. So if you have this non-Hermitian Hamiltonian, which has got an exceptional point of order n, then the eigenfrequencies can be expanded in Newton-Poisson expansion in the inverse powers of this n. In the special case, if n is 2, the second order exceptional point, you can see that whereas you have the energy splitting varying linearly with the parameter theta, in the non-Hermitian case, it has a square root dependence on theta. And what that tells you is that near theta equal to 0, when you make small changes in this parameter theta, you have a huge response of this energy splitting. So that tells you that the non-Hermitian systems, when operated near the exceptional point, and when you change this parameter that controls the degree of non-Hermicity or proximity to the exceptional point, these non-Hermitian systems, they respond drastically to the changes on this in this parameter. Here is an experimentally realizable model where the authors have studied a 3-level system, therefore a third-order exceptional point. And you can see that the energy splitting becomes more and more prominent as you increase the perturbation strength. And here you have a cube root dependence. So that means that near this 0 point where perturbation is very small, the sensor has a huge response to the changes in this parameter, which is like great because it tells you that this non-Hermitian system behaves like a wonderful sensor. But then one can ask, what's the level of quantum noise? How about when these quantum fluctuations become comparable to the degree of perturbation? Would this behavior still exist? And it was shown that in this nice article that even though the energy splitting has a
Sorry to
sharp
interrupt you,
peak.
Javed.
Yeah,
Sorry to
please.
interrupt you. So I think except the speaker, rest all participants, please mute yourself. I think there is some noise constantly, some noise is actually. Please mute yourself, except the speaker.
Okay.
Jikra, please mute yourself.
I'm so sorry.
Yeah, is it okay now?
Yeah, now yes, now you can continue.
So, so in this article, it was shown that even though the energy splitting has a sharp peak near the exceptional point, as you can see in figure C, but the noise, to be precise, the inverse of noise has an opposing behavior and an equally sharp dip. So when you take the signal to noise ratio, which is the figure of merit that one should talk about when you are talking about parameter estimation tasks in such systems, the signal to noise ratio has a smooth behavior near the exceptional point and at the exceptional point itself. So this advantage, this huge susceptibility advantage is completely washed away because of the quantum noise. So this essentially puts an end to this debate of the usefulness of non-Hermitian systems for quantum sensing. But then one can still ask, is there a hope? Can one still do come up with some alternate strategies to harness the power of non-Hermitian Hamiltonians to do some impressive quantum metrology? And this article became a motivation for our work. I don't have time to go into it in detail, but it was shown that one can actually harness the non-Hermitian, the exceptional point advantage of quantum sensors if one introduces some amplification in the system. Instead of going into details of this paper, I'll talk about my results. This model is essentially based on that particular paper, where we consider two cavities embedded with bosonic modes A1 and A2. The cavity 1 has a net loss rate gamma 1. The cavity 2 has a net gain rate gamma 2. A1 and A2 are the probe channels. One sends signals through A1 and reads the A1 out. Similarly, A2 in is an input signal, and A2 out is the output signal that you read. The job is to find the job is to measure these output signals to find some information about some unknown parameter that gets encoded in any of the system parameters. For example, omega-1, omega-2, or the coupling strength G. Any of these system parameters may get perturbed during a process, and your job is to find or estimate that perturbation by measuring the output field modes A1 out and A2 out. The reservoirs B1 and B2 are simply to model the loss and gain rates associated with these two cavities. This equation gives the dynamics of the system, which has both the noise coming from the reservoirs B1 and B2, as well as the probe channels A1 and A2. And the output mode is related to the input mode through this equation 7, a well-known equation, useful equation in such systems. We use Gaussian formalism in this bosonic system, where you can completely describe a Gaussian state by the amplitude and covariance matrix. We compute the amplitude and covariance matrix associated with these outputs that you measure. And once you have as given in equation 10 by the simple formula, the information about the output amplitude and covariance matrix, that means you know the state of these outputs A1 out and A2 out completely. The function G is the response function of the system, which simply tells you how the input amplitude and covariance matrix are related to the output amplitude and covariance matrix that you measure. H is the dynamical generator that was appearing in the quantum Langevin equation I showed you earlier, but here written in the quadrature basis, where J plays the role of an imaginary unit in this symplectic space. This function G, response function, is going to be the central object in this analysis. Now, having this output amplitude and covariance matrix, depending on some unknown parameter theta, one can use this simple formula for a Gaussian quantum Fisher information to compute the Fisher information associated with the individual parameters. Theta here is a bunch of parameters. It can be like more than one unknown parameter in your system. So FJK gives you the jkth entry of the quantum Fisher information matrix. And note that the only information about this theta is actually encoded in this response function. So all the derivatives that you take in this equation 14 are actually the derivatives of this response function G. Now let me tell you about the result. This is in the context of single parameter estimation setting when there is only one unknown parameter. Note that this G theta, if H is a non-singular matrix, if it's an invertible matrix, then this G theta naught tends to a constant quantity. Constant in the sense it doesn't depend on the parameter theta naught itself. So therefore, if G theta is a constant matrix, then the quantum Fisher information is not going to have any dependence on this parameter. So you will have a quantum Fisher information, which is just an independent theta naught independent quantity for small values of theta. So there is no divergence of quantum Fisher information. However, if H is a singular matrix, then you cannot use this Neumann series expansion, but instead something fancier called the San-Massey expansion, where S is the order of pole in this expansion and XK are the coefficient matrices that can be computed by using well-known mathematical formulae, recursion formulae. With this behavior, you can compute the quantum Fisher information, and you can find that it has this theta naught to the power minus 2s behavior. So quantum Fisher information scales as theta naught to the power minus 2s, where s is the order of pole in this expansion. Therefore, the corresponding quantum Cramér bound scales as theta naught to the power s. So what it tells you that the error vanishes as theta naught goes to 0, and you hit the perfect precision at this particular point. Now, the rate at which the Fisher information diverges, or the rate which is given by S, or which is like, say, to put it other way, the rate at which your error goes to 0, it differs according to the choice of the perturbation matrix N naught. For example, if N naught is diagonal, you are perturbing the two frequencies, omega 1 and omega 2 of these two cavities. In that case, the pole order turns out to be 2. So your Fisher information diverges like theta naught to the power minus 4, and your error goes to 0 at the rate theta naught to the like theta naught to the power 2. So it goes to 0 quadratically. However, if you perturb only one frequency, then in that case, the pole order turns out to be 1, and your error goes to 0 linearly with this parameter. This is all in the single parameter setting.
Excuse me, what is the optimal measurement basis? Is it homodyne?
I'm going to talk about that in next slide. Yeah,
Okay,
yeah,
sure,
it will
sure,
turn out
sorry.
to be the heterodyne. Yeah.
Okay.
So yeah, actually double homodyne. Yeah. So in multi-parameter setting, if you have more than one unknown parameters, then it turns out that your error, the scaling of your error is degraded. You cannot do better than the ideal single parameter setting. For example, in this diagram, the black lines correspond to the single parameter estimation, which is a quadratic line in this log-log plot. However, the moment you take one more additional parameter, you end up with these blue and red lines, which are linear plots, linear scalings in this on this log-log plot. And here is the answer to your question. It turns out that heterodyne detection, which is in this case two double homodyne detections on the two output modes A1 and A2, this turns out to be the optimal measurement strategy in the sense that it predicts the same scaling as predicted by the quantum Fisher information. So to summarize, in ideal single parameter setting, you have this Fisher information going like theta to the power minus 2s, where s is the order of pole in the expansion of the dynamical generator. And exceptional pointers do not play any specific role. I didn't talk much about it, but earlier works had claimed that this kind of behavior, this scaling theta naught to the power s kind of behavior, was attributed to exceptional points. But it turns out that that's a special case of this behavior of singularity that I have discussed in the previous slide. In multi-parameter scenario, it turns out that the presence of additional parameters, which are often called nuisance parameters in the literature, they degrade the performance of your sensor as expected. And heterodyne detection turns out to be the optimal strategy in this setup. With this, I thank you for your attention and questions, please.
Thank you, Javed. I think now the floor is open for questions since the next session will start at 7:45. So I think we can take one or two questions.
Sure.
So, Javed, can I ask one more question? By the way, I mean,
Yeah,
thanks for
please,
a very
please.
good talk. So, I mean, when we talk
Sorry, I can't hear you.
about non-hermitian systems, the way that I understand is it's basic non-hermitian systems. The way that I understand is it's open
Yeah.
systems essentially.
Yeah.
And you are not like disregarding some degrees of freedom. You
Sorry,
talked about the
I
Gaussian
lost your
non-hermitian
voice.
system.
I lost your voice. Could you repeat your
Speak
question?
slowly.
Okay, so when we talk about the Gaussian non-hermitian system, so
Yeah.
is there a result that the ultimate system that it comes down from, the ultimate open system that it comes down from, I mean, that system also has to be Gaussian?
Sorry, I didn't get your. The point is that we're using Gaussian probes here in this channel A1 and A2. In principle, you can use any other signal to probe the system, but we're using Gaussian formalism because it is easy to handle analytically.
So because you are it's Gaussian because you are using linear response theory. I mean,
yeah,
correct?
linearity
Okay.
is crucial here. Yeah, of course.
Okay. Yeah. Sure. Thank you.
Thank you.
So, are there any more questions? So, if not, then let's thank the speaker. So, this session is now going to conclude. So
No,
let me
we
thank.
can take questions for other speakers also if someone was not addressed at that time.
Yeah, the floor is open
Thank
for
you.
questions for all the
Yeah.
speakers.
So if any participant wants to ask a question specific to any other speaker, you can also do that, or just even the comments are welcome.
Not question. I just want.
Please continue.
Question.
You are not audible properly. Please continue and speak a bit loudly. You can also type the question if there is an issue in the mic.
Yes.
Who was asking the question? Please unmute yourself and speak slowly.
Hello.
Please continue.
I want to speak to Harsha, ma'am.
Harsha, are you here?
Yes.
Please continue.
Ma'am, can you please provide the references of your talk?
Yes, I can provide. I can provide it in the chat then.
You can, Harsha, you can paste in the chat.
Yes, sir. Yes, sir. Yes, ma'am. Thank you.
Anyone else has any comment or anything? So if not, we take a small break, but please remain online, means you can take tea or water, and then we meet. We restart the session as per time at 7:45 Indian time. But don't leave the room, we'll continue. So we are back, and it's my pleasant duty to introduce the next session chair. So for the rest of the day, or the last session of the day, will be chaired by Dr. Amit Verma. Dr. Amit Verma is an associate professor at JP Institute of Information Technology, Noida, and his research interest includes but not restricted to quantum optics and quantum cryptography. Interestingly, he has interest in both theory as well as in experiment. And with this short introduction, I would like to invite Dr. Amit Verma to chair the rest of the day's session and introduce the first speaker of the session. Dr. Verma, please.
Am I audible? Am I audible?
Yes.
Okay, thank you, Professor Pathak. Now in this session is dedicated to the quantum optics. And in the quantum optics session, our first speaker is Mr. Dr. Kishore Thapliyal, Palaki University, Olomouc. And he will deliver the talk over quantum state engineering of mesoscopic optical fields using photon counting. So again, like the last session, we will have the 12 minutes for the talk and 3 minutes for the question answer session. So Dr. Kishore, you may start now.
So thank you everyone. So to begin with, I will thank Professor Pathak and Dr. Sandeep and Dr. Verma for the conference and for organizing the conference, giving this opportunity to be associated with the young people. And so today I'm going to talk about our recent experimental works on quantum state engineering of the mesoscopic optical fields using photon counting. So I work in Palacky University, Olomouc in Czech Republic. So as I'm the first speaker in this session on quantum optics, so I will have to introduce the non-classical states, which do not have any classical analog, and we identify them by the states which do not have, which cannot be interpreted as a mixture of coherent states. So mathematically, it means that when we write an arbitrary density matrix in coherent basis, so the P function becomes, this Lauper-Sudarshan P function becomes negative or similar than delta function. And alpha is coherent state, which is Poisson distribution of over Fock state. For example, this blue curve is obtained for beta equal to 2 coherent state. So, so if we plot the photon number distribution, we can see the Poissonian distribution. And when we add one photon, we know that the probability of obtaining 0 photon state is 0. And we can check in that case that it gives the P function negative. So in the past, we have worked on a lot of such non-classical state generation of these states in different physical systems. For example, in optical couplers or optical cavities and different kinds of other physical systems. So all these states are useful in different aspects of quantum information processing, for example, teleportation, computation, communication, cryptography, etc. So to begin with, one such example of nonlinear process which generates these states is spontaneous parametric down conversion, in which one firm photon annihilates to generate one signal and idler photon, and energy conservation restricts this. And using the momentum conservation, we know that if a photon is here, so corresponding photon will be here. And so from this, we know if we detect a photon here, certainly there is another photon here. And so mathematically, we can define such output by two-mode squeezed vacuum state, which is in this form a paired photon paired state, where the photon number distribution is given by this thermal distribution, where B is average photon number. And so the quantum state engineering is like where we want to generate or enhance certain properties of a state by tweaking the state, different photon number distributions of the state. For example, if we have a photon, a state xi, and we subtract n photons by using a beam splitter, then this output is photon subtracted state. Similarly, we can add n photons using this process, and so these are all these operations collectively are non-Gaussian operations, which give us advantage in different aspects of continuous variable quantum information. For example, in entanglement distillation, this is the work, and many of these states or operations in the initial stages were proposed by G.S. Agarwal, and some of the initial experiments were performed by Zawata and Bellini's group. And so the experiment on this entanglement distillation was performed by the Takasahi group, and more recently, some other groups have also performed these experiments. So in the past, we have shown the advantage of such operations in some different aspects of quantum information processing, for example, communication, quantum communication, as well as sensing, and we have already discussed sensing in the previous session. More recently, there was a work where they have experimentally subtracted photons using the beam splitter setting that I have just shown in the both beams of two-mode squeezed vacuum. So output of SPDC, they were subtracting photons from the both beams and symmetrically. So when they subtracted 0 photon, we could see the thermal distribution in the black line, which fits the photon number distribution, as I mentioned. And so when they increase the number of photon subtraction from 0 to 1, 2, and 3, we can see that the moves closer to Poisson distribution, which is given in the red line, but still is not narrower than Poisson distribution. So this is what we motivated us to start this study. So experimentally, when we want to generate these mesoscopic states, which are few pairs of photons, for example, in twin beams, few tens to few hundreds of photons, and in such cases we use pulse lasers, and then we have output states which are in different spatio-spectral modes, and we can write the output as mixture of these such two-mode squeezed vacuum states, and the corresponding photon number distribution will be now written for these M such modes. So which can be written as this multi-mode thermal distribution, which is defined by this Mendel-Rice formula, and ideally this will give us paired equal number of signal and idler photon. But in experiments, there is a small fraction of noisy signal or idler photons. So in general, we write this photon number distribution for twin beams. So where there are BP, average photon number, in MP number of paired modes, which is completely paired component, and then there is a small signal and idler noise, which is unpaired but still multimode. So in such states, in such twin beam states, we subtracted photons symmetrically, or we symmetrically added photons in both signal and idler beams. And this is the setting. So we post-select the number of photons here, and we get photon subtracted twin beams here. We post-select the photons here, which heralds the number of photons added in the twin beams in signal and idler modes. So in the subtraction part, we wanted to see whether we can go for the marginal field, generating some non-classicality in the marginal field, because we knew the original twin beam had the marginal field which was thermal or super Poissonian in that sense. So we use two parameters. One is this R parameter, which in the numerator is the variance in the difference of photon number in signal and idler, and the denominator is short noise limit, which is for the coherent state. Similarly, for the marginal field, which is single beam, now we see the variance in the numerator, and the denominator is corresponding coherent state limit. So when these parameters, both R and F, when they are less than 1, so they are non-classical. That means that they have P function negative, as I have shown earlier. So this R parameter is mostly 0 for any transmittivity of the beam splitter used for symmetrically subtracting C bar photons from twin beam. So it remains close to 0 when we were using ideal photon detectors, photon number resolving detectors. And and then we can see this marginal Fano factor becomes less than 1. So we could generate local non-classicality. But we had access to 1/4 detection efficiency detectors. So we could see that in reality, we lose some correlations, but we still have marginal fields having non-classicality. So for this, we use 100 modes with 0.1 average photon number in each mode. But then we went back, why couldn't they could observe that in 2-mode squeezed vacuum? Then we observed that when we took this one paired mode with same average intensity of the beam, and we found that it is relatively difficult to obtain this marginal Fano factor, whether we subtract symmetrically or asymmetrically, because this marginal field, when we take this m number of modes in one, then this is very large and it becomes difficult. But when m is large, then it is already closer to 1. So further subtraction makes it easier to push this below Poisson limit. And so this is from this paper. And so similarly in photon addition, for arbitrary number of photon addition, we could generate local non-classicality without compromising much with the correlations. And this is from these papers. So the experimental scheme was like this, where we had this twin beam generated from this BBO crystal, and we reflected this using this mirror on same CCD camera. And ICCD camera works as photon number resolving detector. And this is for photon subtraction. We had this signal beam and idler beam, and we post select on this DS bar and DI bar to obtain the photon subtracted twin beam in DS and DI detection areas. Similarly, here we had 3 twin beams, and we obtained the photon added twin beam in this area and this area, where post selection is on DS bar and DI bar. So we, as the photon addition and subtraction, these are probabilistic operations. So we obtained these probabilities by repeating the experiment 1.2 million times. And for the experiment, we had close to 50-50 beam splitter. On average, we had 8 photon pairs with very small noisy signal and idler component. And for the addition, we had 3 twin beams with these parameters. And so for the moment, we can just skip through this. But what we can see that what we obtained in experiment is 4-fold 4-dimensional frequency histogram, and we had to invert it to obtain the photon number distribution, where this is a detection matrix, and these are the detail of all the detail. We can skip it for the moment. Similarly, for addition, we again have 4-dimensional frequency histogram, and we obtain the photon number distribution by inverting this relation. So I'll just ask you to focus on this part where we can see the marginal Fano factor is less than 1. And corresponding R parameter is still less than 1. So there are few states for which we have local non-classicality as well as twin beam correlations. This is for subtraction. Similarly, where the smooth curves are from the theoretical model and the data points are given from the experiment with the error bars. So what we can observe here, when we subtract in signal, we lose the non-classicality in signal. But when we subtract from idler, we increase the non-classicality in the signal. So on the other hand, when we do that same from the experiment in addition, when we add a photon in signal, we increase the non-classicality in the signal, but the addition in idler doesn't affect much. But we can see that this is less than 1, and R parameter also remains less than 1. So both subtraction and addition, they give us non-classical
two more minutes.
Yes, thank you. So we have non-classical state which has twin beam correlations as well as marginal field. So we call them Poissonian twin beams, and here we had exploited the spatial correlation to have the detection efficiency, mimic detection efficiency 1. So we have shown the non-Gaussianity of these operations, because as I mentioned in the beginning, so where we use the relative entropy formula for that. So we had, I can skip this, but we put in the one more experiment, we generated the single beam states, for example, the Poissonian initial state as well as multimode thermal state. And we observed that in those cases as well, we performed addition and subtraction. So I would like to summarize here what when we compared the subtraction and addition, what we observe. So for example, this is the theoretical one in the top and the experimental one in the bottom. So we have this two-dimensional photon number distribution. This is signal and idler. And so for example, in this case, when we are adding a photon, we can see there are rows of zeros in the beginning in the signal, and which are visible here in the experimental as well. But when we are, so here it is idler because we are subtracting from signals. So in idler, we have rows of zeros in the beginning, which are reflected in there as well. And then we can see this with the Poisson fit, that it becomes narrower than corresponding Poissonian distribution. And so this was reflected from the integrated intensity distribution which is analogous to P function, but for the multimode states, we can just take the marginal over the phase, and this is just integrated intensity, and where all of them show the negative values for showing the non-classicality of the state. And they have applications in quantum cryptography and entangled virtual state spectroscopy, where the twin beam correlations are used, and we expect that the marginal field, as in this example, if marginal fields have smaller photon number fluctuation, that will give added advantage. So in summary, we discussed Poissonian twin beams, their non-classical and non-Gaussian properties, and compared in case of photon addition and subtraction. So thank you, and these are the references for the works that I was summarizing. And for an extended talk, which was for more than 1 hour, you can go to this link as well. So thank you.
Thank you, Kishore. There is a question in the chat box from the Ashish. And the question is, in the plots for different subtraction rates, what are the beam splitting ratios?
So I will go back. Ashish, can you tell me which one you are mentioning, the experiment?
Yes.
Ashish, please.
Are you telling about this experiment or about theory?
No, sir, experiment. The ones before this.
Ashish, I can't hear you. Can you speak loudly?
Fitting with the Poisson distribution, sir. Fitting with Poisson distribution, that one. In the initial slides, I think 5 or 6.
You mean here?
Slide 5 or 6, sir.
So this one.
Yes, sir, this one. Yeah.
Yeah, so this was performed with highly transmitting beam splitter, and this is older experiment. So because this was not ours, but it was maybe close to 90% transmittivity. Yeah, so actually R is written here, so it is R square is 0.98.
Okay.
98%. But I think, sorry, so this R is actually something else. So it was, if I remember, 90%, but I think I don't remember that because this is not our work. Is there any other
for all the 4 of them?
So it is same because it is from the same experiment. So it remains same. It is post-selection when they post-selected on 0, post-selection on 1, post-selection on 2, and post-selection on 3. But this is symmetrically subtracted from both beams. But the transmittivity of the beam splitter is same.
Okay.
Okay, thank you, Kishore.
Thank you.
Thanks for the nice talk, Kishore. Now our next speaker is Mr. Hemant Hegde. He belongs to Indian Institute of Technology, Dharwad, and his topic is multi-photon operated multi-mode squeezed vacuum states. Okay, you may continue, Hemant.
Am I audible now? Hello?
Yes.
You are not audible. Your slides we can see.
Am I audible now?
Better, but it will be nicer if you can speak a little louder.
Okay, now is it okay?
Yeah, continue. Please continue.
Okay. I am Hemant Hegde. Today I will be presenting my work on multi-photon operated multimode squeezed vacuum states. And our work focuses on two measures, which are like distance measure, one distance measure and one entanglement measure. And we find the bounds for these measures based on the number of photon operations performed on each modes. And we find the necessary and sufficient conditions based on the photon operations performed on each mode to get the bounds of these measures. The distance measure and entanglement measures, those are like different category of measures. They don't have any commonality between them. But in our work, we found one connection between the bounds of these measures based on photon operations. And the distance measure we consider in our study is Bureau's distance. And Bureau's distance captures the Hilbert space distance between two states, rho and sigma, through the fidelity of the states. And the entanglement measure we consider in our study is entanglement entropy. It captures the bipartite entanglement. Suppose we have a state rho 1, 2. The subsystem von Neumann entropy will give us the entanglement, is called as entanglement entropy. And the states we consider in our study are 2-mode squeezed vacuum state and 4-mode squeezed vacuum states. And the photon operated states of like 2-mode squeezed vacuum and 4-mode squeezed vacuum. The 2-mode squeezed vacuum state is generated by applying the 2-mode squeezing operator on 2-mode vacuum state, and the state is given by equation 3. And the photon added state can be obtained by applying the creation operators on both the modes. Here we can see we applied M1 photon operations on the first mode, which is the red curve, and M2 photon operations on the second mode. In our study, we consider we have M photon operations. On those M photon operations, M1 is applied on the first mode and M2 is applied on the second mode. Similarly, the photon subtracted states can be seen using M1 photon subtraction from the first mode and M2 photon subtraction from the second mode. And the equation 5 represents the state. Now, we will calculate the Bureau's distance between these states. The Bureau's distance between 2-mode squeezed vacuum and photon added 2-mode squeezed vacuum state is given using this equation. And for 2-mode squeezed vacuum and photon subtracted state given is this equation. And from these equations, what we can see is when unequal number of photon operations are performed on both the modes, we'll get the maximum Bureau's distance. And when equal number of photon operations are performed, we'll get the minimum Bureau's distance. That is, when unequal number of operations are performed, we'll get the upper bound. And when equal number of operations are performed, we'll get the lower bound. Now we'll move on to calculate the entanglement in photon added and subtracted states, and these are calculated using the subsystem density matrices. We numerically calculate these, and in figure A, we can see as the number of photons added increases, the entanglement also monotonically increases, and we can see for certain combinations of photon operations, there is a lower bound, and certain combination of photon operations, there is an upper bound. Now we'll consider 4 photon operations, that is m equal to 4, and those 4 photon operations can be divided like this, where like the odd, some m1 number of operations are performed on odd mode and m2 number of operations are performed on even mode, and 4 photon operations are divided like 0, 4, 1, 3, 2, 2, 3, 1 and 4, 0. Here we can see when equal number of photon operations are performed, we'll get the upper bound of entanglement entropy, that is when m by 2 operations is performed. And when all the photon operations are performed on either of the modes, then we'll get the lower bound, that is 0 and m0 will give us the lower bound. Similarly, in case of photon subtracted states, we can see certain combinations will give us the lower bound and certain combination gives us the lower bound, upper bound. And same as photon added states, the m by 2 operation, that is equal number of operations on both modes gives us the upper bound, and unequal number of operations, that is 0m and m0 operation will give us the lower bound of entanglement entropy. Now, what we found out is when equal number of operations is performed, we will get the maximum entanglement, but the corresponding distance between those states will be minimum. And when the entanglement is minimum, then the distance will be maximum. This is the observation we have, and This observation we will try to see in multimode states, and in multimode states we consider the photon added 4-mode squeezed vacuum and photon subtracted 4-mode squeezed vacuum states. Now first we will consider the distance between photon added 4-mode squeezed vacuum and photon 4-mode squeezed vacuum and photon added 4-mode squeezed vacuum. Here we can see the condition M1 equal to M2 will look like M1 plus M3 equal to M2 plus M4. The M1 is the number of operations performed on mode 1 and M3 is the number of mode operations performed on mode 3, and combined mode 1 and 3 we will call as odd block modes, and M2 and M4 are called as even block modes, and M2 and M4 operations are performed on those. That is, when unequal number of operations are performed on odd and even blocks, then we'll get the upper bound of Bureau's distance. And when equal number of operations are performed on odd and even blocks, we'll get the lower bound. And same is compiled here. And unequal number, we'll get the upper bound, and equal, we'll get the lower bound. And in case of photon added 4-mode squeezed vacuum states, the equal number of photon operations will have like many combinations are possible for that equal number of photon operations. That is, when that m/2 photon operations in even block will have many combinations. In particular, the m/4, m/4, m/4 operation will give us the lower bound. And similarly, in case of photon subtracted states also, same conditions we will get, though the coefficients and this will be different, we'll get the same condition, and the unequal number of operations will give us the upper bound, and equal number of operations will give us the lower bound. Now we will move on to calculate the entanglement entropy in these 4-mode states, photon operated 4-mode states, and it's already showed that though there are like many bipartitions possible and entanglement entropy can be calculated in many bipartitions, it is sufficient to consider 1:2 rest, that's 1:2, 3, 4, and in 2-party bipartitions, 1:2, 4, and 1:2, 4, and 1:3, 4 bipartitions are sufficient. Then we will cover all the bipartitions. Now we will start with 1:2, 4 bipartition. This is 1, 3, and 2, 4 in different blocks. Therefore, this can be seen as odd is to even bipartition, and these two are the reduced density matrices. From this, we will calculate the entanglement entropy. And here also we can see entanglement monotonically increases, and certain combinations will get the upper and lower bound. Now we will take m equal to 4 photon operation, and that for m equal to 4 photon operations in 4 mode, the m1, m2, m3, m4 will have lot of combinations, and those combinations can be divided such that m1 plus m3 operations are performed on even block, and m2 plus m4 operations are performed on odd block. Then we can divide all the combinations such that 0, 4, 1, 3, 2, 2, 3, 1, and 4, 0. Now we can see that for combination 2, 2, we'll get the maximum entanglement, and in the combination 0, 4, and 4, 0, we'll get the lower the lower bound of entanglement.
Hello. হ্যাঁ হচ্ছে তো আমি যে বললাম ডাউনলোড করে নে জুমাকে ডাউনলোড করে নে
Please unmute yourself.
ডাউনলোড
Please
করে
mute yourself apart from the speaker.
Okay, now we can see in the case of photon added 4 mode.
Hemant.
Okay.
Yes.
When equal number of operations are performed on odd block as well as even block. That
Hemant.
Hello.
I have one question.
Yeah.
In this F diagram, the magnitude means the value of highest peak is also relevant with our earlier result or not? Because
okay. That result is already studied like in the reference I showed earlier. In that one, they have showed that in photon subtracted states will have higher entanglement than photon added states. That is studied. In our work, we focus on the combination for which we'll get the entanglement.
Okay, carry on.
Now, when equal number of operations are performed on odd and even block, that is m/2 operations are performed on even and odd block, then for this particular combination, that is m/4, we'll get the upper bound. And similarly, when unequal number of our operations, particularly 0m and m0, and
two more minutes.
And in particular, all the photon operations are performed only on one of the modes, then we will get the lower bound. in case of photon added 4-mode squeezed vacuum states. And in case of photon subtracted states, only the equal number of photon operations on odd and even block is sufficient to get the upper bound, and like unequal operations such that 0M or OM0 operations on odd and even block will give us the lower bound. And we extended this study to other bipartitions also, but the most interesting will come from the odd is to even bipartition. And in odd is to even bipartition, here also we can see the lower end, like the lower bound of entanglement will corresponding to maximum distance, and maximum entanglement will correspond to minimum distance, both in the case of photon added states as well as photon subtracted states. And I will conclude our work, and like in the conclusion, what we found is like based on the number of photon operations on like each modes, we can get the necessary and sufficient conditions on bounds of distance measure and entanglement measures. And in odd is to even bipartition, the minimum distance state will have the maximum entanglement and vice versa, and maximum distance state will have the minimum entanglement. This concludes my talk. Thank you.
Thank you, Hemant. Now, any question? Beside that, there is one question in the chat box from Mr. Vishal. How can entanglement entropy be used as an indicator of phase transitions in your system?
Okay, I haven't come across like entanglement entropy as like a phase transition indicator. If somebody knows that, then I haven't come across it.
Okay, once again, thank you, Hemant. Now let us invite our next speaker, Mr. Sudeep Chakrabarti. He belongs to SN Bose National Center for Basic Sciences, and his title of the talk is Efficient Detection of Non-classicality of Continuous Variable States Using Moments of Wigner Function. Welcome, Sudeep.
Hello, I am audible.
Yes.
Okay.
Maybe some people are like trying to do something else.
Okay. So today I will talk about efficient detection of non-classicality.
Hemant, please mute yourself. Hemant.
We never come across that. Like maybe people try to do that also.
Okay, may I start? Okay.
Yes, Shruti, please continue.
Yes, you continue.
Okay. So today I will talk about efficient detection of non-classicality of continuous variable states using moments of Wigner function. I will describe the terms from basic, the term non-classicality, continuous variables, and also the moments of Wigner function. And this is a brief outline of my talk. In the introduction, I will talk some mathematical preliminaries and motivation why we need to do this kind of work. Then I will go to our work, where I will talk about Wigner moments and our detection criteria. Then I will propose something experimental kind of stuff that we can do with already proposed stuff in literature. And I will conclude with a brief summary, and then question and answer will follow. So till now, many people has already talked about continuous variables. So in quantum information theory, we can broadly divide it in two categories. In discrete variables, we talk about qubits, spin degrees of freedom, so on, where the degree of freedom is finite. And in continuous variable, we talk about situations where we have continuous eigenspectra, for example, position, momentum, or the vibrational degree of freedom, and so on. And this situation can be described using the infinite dimensional Hilbert space, and that can be described using the Fock basis. They are just the eigenstates of the quantum harmonic oscillator. And as a prototype, we can use the quantum harmonic oscillator. For example, in classical situation, if we have a well-behaved oscillation, we can break it down in Fourier analysis into sinusoidal terms, which are just the solutions of the classical harmonic oscillator. And they're represented by their specific frequencies. In quantum situation, we can use this kind of Hamiltonian, where we add up the Hamiltonian for the quantum harmonic oscillator, and each term is represented by the creation and annihilation operators. They tells us the mode of that specific term. And we can go to quadratures using this kind of transformation. Here x and p are just the position and momentum quadratures. And with those position momentum quadratures, we can go to a different kind of representation called the phase space representations. There are many. I will talk about only Wigner representation. Now, the Wigner function is just mapped from the density operator to a function. This way we can go from rho to WXP, and this is a one-to-one map. That means if we know one, we can go to the other. Now, since W is a function, we cannot use the operators in quantum theory directly. We need to use a map that takes the operator to the function, and that is given by this Weil transform. And we can see that Wigner function is also a map that takes the density operator to Wigner function. And here the first few Wigner function for the Fock states n equal to 0, 2, 3 are plotted. And in Wigner picture, we can get the exact expectation value of some operator or the observable using this kind of equation that somehow looks similar to what we do in classical physics. Now, there is a big question from very early years of quantum physics, that where is the exact boundary between classical and quantum physics? And to answer that, if you look at classical experiments, we take suppose we're doing an experiment, we take the data for quite a large number of trials, and then we take the average values, and then it becomes just the observable times the probability that outcome came, and then we take the sum. And for continuous outcomes, instead of discrete probabilities, we take the probability distribution and the observable as a function of the variables, then we take the integration, and then we get the expectation value. But in quantum mechanics, if we try to use the same equation, we see that there is some differences there. The probability distribution function goes to the Wigner function. And the main difference is that the Wigner function can take negative values. So it's not a probability distribution anymore. So there we get a boundary. If W is positive, then it's exactly a probability distribution, then it's classical. And if it can take negative values, if it takes negative values, then there is no classical counterpart. W is then called a quasi-probability distribution. And in my talk, non-classicality basically means the presence of negativity in the Wigner function. Now, people can ask that, well, there is some differences. This is quasi-probability, but why it is important to detect the Wigner negativity? The main reason is that there was one result by Mary and Isaac, that is the generalization of Gauss-Mann-Niel theorem from quantum computation. And they showed that if we use a Wigner positive function and do operation that preserves the Wigner positivity, then whatever we do, whatever be the entangled measure of that state, we can do everything using a classical computer. So what is the need for a quantum computer? So it becomes a necessity to use Wigner negative states in quantum computation. And there is also follow-up works like quantum computational speedup. And also it has been shown that if there is Wigner negativity, then it gives us advantages in various information processing tasks. And recently it has been shown that Wigner negativity and contextuality, they are actually equivalent. Now, to detect Wigner function, the Wigner negativity, we introduce the concept of Wigner moments. And this is a very simple concept. We take the nth power of the Wigner function, then we integrate over all the quadratures, and whatever be the number of modes, here we have written in 2 modes, but that is not necessary. Now, then we start our mathematical stuff, we start from Wigner positive function, then you use the LP space and use the Cauchy source inequality kind of thing. And after a lot of mathematical stuff, we get to this condition, omega 2 square less equal to omega 3, and that is a necessary condition for Wigner positive function. Now, when a necessary condition is violated, we know that we get a sufficient condition for the opposite result. So if this criteria is violated, we sufficiently get, or we can comment that the state must possess Wigner negativity. Now, for example, if we talk about Fock states, the ground state is a Gaussian state and it is positive, we know, and it is shown by our criteria that it does not violate our criteria. And all other Fock states from n equal to 1 to any n greater than equal to 1, they violate our criteria. And we can see that from the plot as well. The ground state, the plot with A, that is Gaussian, and the states with n equal to 1, 2, 3, they are non-Gaussian and also Wigner negative. And we can see that they have negative regions. And for the second example, we can consider the known states where we have n photons in a mode and there is 0 photon in the other mode. It's a 2-mode state. And with this state, we can calculate the Wigner function and then we can check whether they violate our criteria or not. And we found that for all n greater or equal to 1, they violate our criteria, hence they are Wigner negative. Now, if we compare with other known methods to detect Wigner negativity, for example, witnessing Wigner negativity, they are state dependent. Or the other way we can do tomography to get the Wigner function in direct way or indirect way. In the direct method, we construct the Wigner function directly. In the indirect method, we first construct the density operator, then we do Fourier transform to get the Wigner function. But the advantage in our scheme is that we need to calculate only simple functionals. We need to calculate only some integrations to know whether there is Wigner negativity or not. And the second advantage is that, so for doing tomography, the number of states and the measurements required are exponential. But since we are not trying to know the Wigner function exactly, we're just trying to know whether there is Wigner negativity or not, we need very less number of copies. That's polynomial in the number of mode of the system. And finally, our method is state independent. So no prior knowledge is needed about the state. So that is some advantage over the witness stuff. Now, the experimental proposal. So it has been recently proposed, the continuous variable swap operator by Volkov in 2022. And that looks like this way. Well, they represented it using the using the creation and annihilation operators, but it can be written using the quadratures. Now, how it operates, it just swaps the creation operator from mode 1 to mode 2, and the action is clearly written here. Now, to use the swap operator in the Wigner function formulation, we need to use the while form of that operator, and that is given by this expression. And this is not the exact expression. We need to do the integration, then we get the form of the while form, then we can use it using the Wigner formulation.
Sudeep, 2 more minutes.
Okay. Now, in the experiment, what it has already been proposed for to detect the partially transposed moments, and there it was proposed by Johnny Gray, Shogoto Bose et al. In 2018. Now, to realize the second order moment, we need two copies of the state. So the tensor product over 2 that represent that we need 2 copies. Then we can use the while form the swap operator, and this gives us directly the second order moment. And it's been shown that the swap operator is experimentally realizable by Volkov. And for the third order moment, we can use the permutation operator of order 3 that is represented by FP3. But the advantage is that this permutation operator can also be written using swap operators. The order, the sequence has to be accurate. For example, we are talking about two mode situation. So there are, and also we are using 3 copies. So there is Alice 1, Alice 2, and Alice 3. Then there is Bob 1, Bob 2, Bob 3. Now in the Alice part, if the swaps are done in this order, Alice 1, Alice 2, then Alice 2, Alice 3, then Alice 3, Alice 1. Now in the Bob's part, it has to be done in the opposite situation, that is Bob 3, Bob 2, then Bob 2, Bob 1, then Bob 1, Bob 3. And if we follow the sequence, then we can readily write that FP3 using the swap operators, and we can realize the third order moment in experiments. So since we can realize the moments W2 and W3 in experiment, we can actually detect our criteria and we can comment whether the state is Wigner negative or not, and whether should we use it for quantum information processing task or quantum computation or not. And that requires very less number of measurements. So in conclusion, we have introduced the concept of moments of Wigner function, and we have also proposed the criteria how can we detect the non-classicality, that is here Wigner negativity, using those moments of Wigner function. Then we have given some examples, some in the talk, and some more examples are there in the paper. And finally, we have shown how we can experimentally realize the moments using the continuous variable swap operator, and that establishes our protocol's experimental feasibility. Thank you.
Okay, thank you, Sudeep. Now there is the question session, and in the question session, there is the first question from Asis. Asis, please, you may ask.
Thank you, sir. So to get the Wigner moments, we need the Wigner distribution. So again, to get the Wigner distribution, we need the quadrature data. So and for that, is there a, and again it comes back that you need to either perform get the quadrature data, do an inverse data transform, or do the tomography, get your density matrix, and then do a Fourier transform.
No. Actually, in the experimental kind of thing, experimental proposal, we showed that we need 2 copies, but we don't need to know the Wigner function. We can actually cite that part. We don't need to know the state or the Wigner function. We will just know the moments. So in mathematical proof, we used all the data, but that is true mathematically. But experimentally, we don't need. We did the mathematical stuff just to get to the criteria.
So experimentally, let's say we are in the case of a measure experiment, what are the things that we need to measure here? Like quadrature data, but for like, is there a way in which you can reduce the number of measurements to just get the moments, or is that the correct way in which
actually, you are not doing the quadrature measurement here. So the swap operator, there you don't require the quadrature measurements. You can look at that Volkov paper. Actually, it's experimental one, but there you can see that you are not actually measuring the quadratures.
Okay, thank you, Sudeep. You may connect Ashish. You may connect with Sudeep directly. Second question is from Professor Sur. Yes, Chiranjeev Sur, and please, Chiranjeev, you may ask directly to the Sudeep.
Hi. So the relation that you had with 2 moments, so basically it's a relation between the second and third moment, right? And it's a sufficient relation for Wigner negativity. But now, I mean, your approach, what it seems like, I mean, you can basically do any moment that you like. You can do 8th moment as well if you have 8 copies of the system.
Yeah. I can.
So now,
any
instead
moment,
of only, I mean, relation between 2 and the moment 2 and moment 3, you can have like a progressive chain of inequalities with higher moments, which bounds the system
we are
more.
trying to do that.
So
Actually,
can you do like a complete detection with that? Yeah. Okay.
Yeah, we are doing that. That is the work I'm doing right now. That for example, if we are talking about mixed states, then though our criteria is sufficient, but that is not that good. Many states which are Wigner negative, our criteria cannot catch them. But when we increase the moments, then it is the simplest one. with
So
third
the
order
sequence
moment.
of moments that we have,
Yeah.
I mean, apart from this, so is this sequence finite, or do we have an infinite sequence of moment relations to actually, I mean,
No, we don't
ideally
need to go to
bound the
infinite.
complete thing?
We don't need to go to infinite sequence. So actually, we can get the optimal criteria using finite number of moments.
Oh, amazing, amazing. Thank you. Thank you. Great talk.
Thank you. Thank you. Thank you,
Hello.
Chiranjeev. Thank you, Sudeep, for
Yeah.
a nice talk. Now,
Hello.
Oh, it seems
Yeah.
there is another question.
Yeah. Thank you so much for the talk. I have one question. This might be a stupid like question. I'm not very much familiar with this function. So my question is that if the function gives exactly 0 values, then what does it signify? It is something like quantum interference, or this cannot be concluded anything.
Well, if there is a zero outcome, then we actually cannot comment about Wigner negativity. Because for Wigner negativity, violation is required, and that is not less equal. That is exactly has to be positive. That is greater than 0. Then we can comment.
Okay, so then for this case, we just can't conclude anything else, right?
We cannot conclude anything.
Okay, okay. Thank you so much.
okay, thank you so much. Now let us welcome the another speaker, Mr. Ram Krishna Patra. He is also belongs to SN Bose National Center for Basic Sciences, India. His title of the talk is Non-Local Locking of Observable Quantities, a Faithful Signature of Non-Classical Correlations.
Hello, am I audible?
Yes, please
You may
continue.
start, Mr. Ramakrishna. Thank you.
Yeah, okay. The screen is visible, right?
Yes.
Yes,
Okay.
but it's not full screen mode. I can see your slides still.
It's now it's in the full screen mode.
No.
No, but you can just, there may be an issue, but you just change the slide and check.
Oh, okay.
It's in slide number 1. Okay, it's working. Please speak.
Okay. So today I'm going to talk about this non-local locking of observables. But first of all, I'd like to thank the organizer for giving me this opportunity. So today I'll briefly discuss what is correlations, what do we mean by non-local locking of observables. And this work is mostly based on our recent work that is available in arXiv. So let's start by first discussing what do I mean by non-classical correlation. So correlation is nothing but there is some property hidden in the state such that if you want to measure that property, there is a difference between the global value of that property and the local value of the property. So the observable values are different. For example, what do we mean by global probing? Let's say you have some system. Let's say there are 3 particles and you want to extract some value. So F is a map which is actually giving you from that state some observable quantity alpha, which is some real number. So this is a global probing. You are extracting the value globally from the state. And what do you mean by local probing? Let's say this same state is there, but now there is a single party who is applying the probing in this local part of the system and extracting some value. So now individually all of them are extracting the values, and now we are claiming that the global extracted value alpha is actually greater than all the summation of this locally extracted value. So if there is a difference, then it will imply that there is a correlation in the systems. So what do you mean
Excuse
by
me?
non-classical? Yes, hello.
I think your slide is not moving. I cannot see it.
It's not moving. Oh, just a minute. Just a minute.
Also make it full screen, please. This is not full screen mode.
Click slideshow. Click slideshow.
Yes.
Yeah, actually.
Slideshow.
Okay.
And then click from the beginning.
Is it moving now?
It should move now.
Is it moving? No, I think it's not moving. Just a minute.
Actually, no.
Just a minute.
It seems that there is some issue in your full screen mode, slideshow mode. You don't use slideshow and you just open one by one slide or share your full screen.
Is it
This is your
visible?
first slide, means I can see the archive.
Yeah, now can you see this slide?
I can see the correlations.
Yeah. Okay, so maybe there is an issue with the full screen mode. Maybe I'll just talk from here only. Okay.
Please continue.
Yeah. Okay. So what I'm saying is that in the terms of correlation, I was saying that okay, you are actually globally probing the systems, and from the global system, you are extracting some value, this alpha, and from individual locally systems you are probing, and you are getting this. The first part is extracting the value alpha 1, second part is extracting the value alpha 2. So there is a difference between this global accessible value and this locally accessible value. So correlation will actually lead to some difference between the total observable values. But this is a local, means classical correlations can also give these kind of things. But what do we mean by non-classical correlations? So actually in case of non-classical correlation, what happens is that you already have this global probing where you are probing the whole system. But in the other cases, you are probing the system with the help of LOCC. What do you mean by LOCC? That there is a communication between the parties. They can talk and they can share classical bits, and after that they are probing their own individual systems. So if there is a difference between the global and LOCC scenario, that implies that the system is in some sense non-classical. So next I'll come up to the some example of non-classical correlation. One is quantum entanglement. So the states which can be written as the separable, this convex mixture of this separable state, this rho AB, that actually means that the states have zero entanglements, which the quantum state which cannot be written like that, they are entangled. And then what are the discord states? So the discord states, the definition can be given here. It is shown. It is nothing but there is actually difference between two equivalent classical definition of mutual information. So the amount of discord is actually defined by this, where the party A is actually probing the system with respect to this measurement pi A, and he is trying to get the as much possible information about the other systems. So in general, in classically, these two are same, but there is a difference in case of classical. So those states are called quantum discords. So actually, if you look at very carefully through the state space structure, there is a difference between the set of entangled state and the set of discord non-zero state. This is just a graphical representation because none of them are actually convex set. Okay? So the discord non-zero state are actually bigger than the quantum entangled states. So next I'll come to the operational framework of this thing. So let's say I am probing my system individually using this from individual system. I'm accessing some value. Let's say I'm getting the value of some observable as alpha. But as I have the local system, I can actually apply some local map on my system. I can transform the system to some other things. So let's say I apply this map phi and I get the evolved system. So now I can get the observable value from this evolved system as well. And let's say the value is alpha A prime. So now what I can do is that I can define that, okay, let's say there are a set of operations or map that I can apply locally in my lab, and I want to optimize over all those map, how much value I'm extracting. That quantity we are defining by this delta of f given phi A, which is nothing but the optimization over that set of map. And now you can do the same thing for the global extracted value, where you are defining some global map, you are evolving the system globally, and then you are extracting the values. Now we are defining a quantity that is known as FGL, that is the difference between these observable quantities when you are extracting them globally versus when you are extracting them locally. And this is under the this is also maximum that you can apply globally as well. Sorry, is there any question?
Dr. Ekta, yes.
So I'll continue. Okay. So okay, now let's come to the next thing, like how to operationally implement these things. Like let's say I'm saying locally I'm extracting some value, globally I want to extract some value. So globally what you can do is that if you have the whole system, you can actually get the value from the whole system. But now let's say you are spatially separated, so how you will extract the global value? So what you can do is that there is, let's say, some identity quantum channel between the first party and the second party and the third party and the second party. So both of them are sending their qubit to the party and he is actually extracting the value. So ideal, if you want to implement it experimentally, there should be some quantum channel between the parties. So now let's come to one example where we can actually get up with these ideas. So we are saying, okay, let's take this choice, particular choice of f gamma and phi gamma. What is f gamma? It is nothing but the amount of purity extraction. That means that given a state, bipartite quantum state, how much amount of how much amount of purity you can extract from that state. So if you define the f gamma to be that log dy minus s of rho gamma, and the set of operations that you can apply in your lab locally, those are nothing to be the noisy channel, then you can actually show that this global versus local difference is nothing but this s rho 1 plus s rho 2 minus s rho global, that is nothing but the mutual information, quantum mutual information I of a1 between a2. So this is one example. So now we can move towards developing the resource theory of quantum mechanics. What is this resource theory of quantum mechanics? So in the any resource theory, what you have is that you have to define is free state, like the states which have the zero values for the resourceful properties, and we will define the free operations, like operations which map the set of zero resources to the set of free states. Okay. So now let's come to the resource theory of Discord. So we already know that which are the Discord zero states that I have already defined previously. These are the Discord zero state. From Alice to Bob, the Discord is zero. I am particularly considering that Discord. And what are the free channels? Like what are the free operations in that case? Like Alice is sending the state from his part to Bob. Like then what are the free operations that he can apply that which will not increase the Discord? So those are nothing but actually measure and prepare channel. Like you can think in this case that the first particle is measured in the this pi L projector. You are actually measuring them and you are preparing them in the sigma L, which are nothing but some orthonormal basis. So this is a
Ramkesh,
measure and yes.
please, little fast. You have three
Yeah,
more
yes, yes,
minutes.
yes, yes.
3 minutes.
Yes, okay. So now we'll go to the resource theory of Discord, where we are saying that okay, you can actually take this purity extractor, and the operations could be noisy operations, and this operation, the channel that I defined, which are free, actually you can use them as a free channel, and we are showing that that global difference can actually faithfully capture the measure of quantity of the Discords, which are only the catch is there, the mixed marginal part should be the maximally mixed for the A1 system. So what we have shown that if you extract the work globally and if you extract the work locally, and you can actually capture the measure of the Discord using this noisy channel and taking together. So now I'll come to the quickly to the last part of my talk, that now we are going to the resource theory of thermodynamics, where we are saying that okay, you have a bipartite state and you apply some global operation UAB and you extract the work. This work is the ergotopic work that you can extract globally. But now we are saying that okay, instead of that, let's say there is a free channel and Alice is applying some local unitary and extracting the work, then he's sending through the channel, and then Bob is applying the global system on them and extracting the work. So that we are terming as ergotopic work, LOCC. Now we are showing that what are the free channels that you can use here, because now it is another observable quantities. So free channels are nothing but those basic criteria that after the action of the channel, the observable quantity should not increase, as well as the difference between the global and local should not increase. Those are the criteria in C1 and C2, nothing but. And we have shown the particular form of the channels that can be. This is nothing but the measure and prepared channel. And then using that, we have shown that this difference between the global and local for the observable quantities will faithfully captures any non-classical correlations. Now you don't need that condition given that the observable has non-degenerate spectrum. If there is degenerate spectrum, this is not applicable. And now we have applied that for particularly qubit systems with 2-qubit system, bipartite 2-qubit system, and we have given some closed letter formula to calculate these differences, and we have plotted them for the Warner states, and we are showing that okay, our measure is actually monotonically increasing with the Discord value. So I will conclude with the open problems, like what I said, that above measure, is it a proper measure? So it is not actually proper measure. Any measure should satisfy these three quantity. It must be faithful, it must be invariant under unitary, and monotonically decreasing under Bob operation. So we are able to prove the first two things, but we are not able to prove the last things. So in some sense it is a signature of the non-classical correlation, but it's not a measure. And the second thing is that whether it is independent of the Discord or not. So that we have not still proved. We are looking for that. Thank you.
Thank you, Ramkesh, for a nice talk. Any question? Okay, now let us welcome Devi Bala, School of Physics, Madurai Kamraj University, Tamil Nadu. Her title of the talk is Heralded Generation of Displaced Qubits from Quantum Optical Catalysis. You may unshare, Ramkrishna, you may unshare your screen.
Yes, yes, I have.
Okay.
Am I audible?
Just wait, just wait. Before starting this talk, there is one announcement in the chat box from Professor Pathak that this conference is supported by Springer, and we would like to announce that a special issue of quantum information processing with the title Quantum Information in India will be published in 2025. So you will be updated from the Springer team. Okay, Miss Devi Bala, you may start your talk now.
Yeah. Is my slide changing?
Yes.
Yes,
Yeah.
it's working.
Yeah. Good evening, everyone. Today I am going to present our recent research work on the topic of error generation of display units from quantum optical catalysis. So this is the contents of my present.
Dr. Ekta, please mute yourself. Thank you. Devi Bala, yes,
Yeah.
you may start.
Yeah, this is the contents of my presentation. First, let me introduce what is conditional measurement. Generally, if we need to extract any information from which is encoded from any signal mode, we have to send that signal mode to the beam splitter, to one part of the beam splitter along with some classical sheets. So by means of projecting one output mode, we able to get the information which is carried out by the signal mode. So by means that the other output state remains unobserved. So in 1994, Ban studied this unobserved output state, and he assumed that it must obey the projection postulate of quantum mechanics. So he studied the photon statistics of this unobserved output state, and he noted the quantum mechanical behavior. So this quantum state of the unobserved output state, which is affected by the detection of one output mode, is named as conditional measurement by Ban in 1996. So, followed by Ban, numerous studies have done by Dagna et al. By changing the input state as squeezed vacuum state, and the projection state as replicate number states, and study the output state of conditional states. And they have changed various states like input states as photon number states, and detector state as various photon number states, and they have studied the photon added or subtracted Jacobi polynomial states. And followed by them, Lavorsky et al. Studied the output of that specific conditional output as by fixing the input state as single photon state and the detergent state as single photon state. So he named the setup as quantum optical catalysis. So this is a simpler pictorial representation of quantum optical catalysis. They sent a coherent state and a single photon state to the two input port of beam splitters, and they detect a single photon at one output port. By means of that, they able to generate a superposition state. So here the single photon state is involved in the process and simultaneously detected at output port. So this single photon act as a catalyst to generate a new quantum state. So by means of that, they named this setup as quantum optical catalysis. And it is a subclass of conditional measurement where the input and detector state are same. Then without any addition of photon or subtraction of photons, QoC can generate various quantum states by it can produce effective non-reality in the system. Then some non-classical operations are studied along with quantum optical catalysis protocol, such as hole burning to generate some holes in the PND distribution, and like fog filtration to remove some fog state from the PND by fixing the reflectivity of beam splitter as Rm equal to m by m plus 1, and photon catalysis like multi-photon catalysis, and cascaded arrangement of beam splitters to remove photon replacement setup. Then further, they have extended the multi-photon catalysis by Botley et al. In 2012 Then the output of this state was studied as Laguerre polynomial excited states. They have characterized the output state with the different polynomial states. First is Laguerre polynomial excited states, and in 2017, Cruz et al. Studied this output state as a continuous to discrete variable converter. Recently, in 2019, Miller et al. Have studied to produce a GKP state by using condition measurement setup. So our objective is to write such polynomial states to QRIT's representation to facilitate the quantum information protocols and to study the production of exotic states such as displaced number states and superposed states, and to visualize the bin splitter operation and condition measurement, and to characterize the non-classical properties such as squeezing, non-Gaussianity of the states, and to simplify the optimal parameters of the desired states. So displaced qubits. So this is our consider setup. We have sent a coherent state along with multi-photon number state to the two input ports of beam splitter. By the deduction of same photon number state at one output port, we able to create a displaced qubits at another output port. So this is the representation of displaced qubits, and AMP is the superposition coefficient, and D of alpha is the displacement parameter, and this is the superposition coefficient expression we arrived, and here it represents the qubits where M replaces the D dimension in qubits. Then displaced qubits, though the normalization constant of the displaced qubits is given here. For different input states, we have derived these states, like for single photon states, we are able to get displaced qubits. For 2 photon states, q tris. For 3 photon states, q quads. So basically, quantum optical catalysis can transforms the state into two forms, like the input coherent noise will be reduced to alpha root dot, and there will be some phase rotation is induced in the system. Like the Laguerre polynomial terms always possess negatives in the odd integers, so it causes some negative phase rotation in the system. And here we are going to derive the conditions between superposition coefficients and chi, where chi is represented as mod alpha square into 1 minus r. This relation plays the vital role here. Then, so first displaced qubits. For the single photon state input and the detection of single photon at QC process, we able to create displaced qubits at one output port, and the superposition coefficients are given here. We have plotted the amplitudes of superposition coefficient with respect to coherent amplitude and reflectivity of beam splitter. Here, this dash curve represents the root of K0 and simultaneously unity of K1. So these values are comes along the condition of chi equal to 1. That condition, the state becomes displaced K1. So this green line represents the root of K0 and the unity of K1. This is the overall figure of superposition coefficients, and for the relations of alpha given here, the sum in the relationship we can get the sum of equal superposition with the displacement. For the difference in this equation, we are able to create negative superposition of K0 and K1 with displacement, which is shown as orange curve in this here. And for to create displaced qubits, we have to send 2 photon state at input port and detect the 2 photon state at on output port in quantum optical catalysis processes. So by means of that, we can create the displaced qubits, which is given here, and the coefficients are calculated as here. So these are the coefficient amplitudes plots are shown. For K0, we have 2 roots which lies under the condition of chi equal to 2 plus or minus root 2. And for K1, there is a root and there is another unity of getting K1, which lies under the condition of root lies under the condition of chi equal to 2, and K1 is chi equal to 2 minus root 2, which is shown at another slide, where chi equal to 2 minus root 2, we are able to get this much of displaced K1 state. Here, this displacement produced is slightly diminished than the displacement produced in the displaced qubits. So if you need more displacement parameter, we have to go to displaced qubits rather than displaced qubits for getting displaced gate1 state. And for chi equal to 2 plus root 2, we can create superposition states of gate1 and gate2 along with displacement. And for chi equal to 2, we can create displaced even superposition states, that is gate0 and gate2. Further, we have studied the non-Gaussianity of the creator state displaced qubits by using the measure called Hilbert-Smith distance. This is the expression to obtain Hilbert-Smith distance. If the delta of rho is greater than 0, then the exam state is considered to be a non-Gaussian state. So here the dark blue region shows the non-Gaussian nature of displaced qubits. And here the optimal case is found to be for displaced qubits it to be displaced gate1, for displaced qubits it to be displaced gate2, and for displaced qubits it's qubits is displaced gate3. So other than that, the two sub-branches and three sub-branches belong to the superposition states, where when the vacuum state is absent, there must exist and non-Gaussianity in this state. So we further study the quadrature squeezing by using the variances in the quadratures. So these plots represents the squeezing nature of displaced qubits. In qubits, the optimal squeezing lies under the generation of eco-superposition states, whereas in qubits and qubits, it lies under the generation of even superposition states, that's gate0 plus gate2. And we further studied the realistic generation of displaced qubits by taking the experimental imperfection of photon detectors and photon sources by using these formulas. Here NDA represents the photon detector inefficiency and eta S represents the photon source inefficiency. The non-ideal DQ state can be calculated by using the expression here, and we have calculated the fidelity between the ideal density operator and realistic density operator to show the difference in experimental imperfections. So here we have plotted the displaced qubits experimental imperfection fidelity. So by observing these plots, it is observed that photon source inefficiency affects experimental relaxation than photon detector inefficiency. Then success probability, we have studied the success probability of generating the displaced qubits, and by comparing with ideal cases, the overall performance is reduced to 20% than the ideal cases for the photon source inefficiency and photon detector inefficiency 0.9. Then summary, experimentally realized process quantum optical catalysis is used as a technique to generate displaced qubits, and superposition coefficient calculated or facilitated to the creation of diverse multiple states from displaced qubits, and the optimal non-Gaussian of DQ is achieved by generating individual displaced number states. Meanwhile, the optimal degree of squeezing of DQ is achieved by generating superposed states, and DQ indices the degree of squeezing in the system. Non-Gaussianity of the input does not get enhanced, but it spread wider in the regions. And a non-ideal generation of DQ is accounted to facilitate the experimental realization. So present focus of our work is multimode extension of quantum optical processes, which is shown here, and already it has been studied that two-mode extension of the conditional measurement by Kumar et al. And Britla et al. So it is shown here. Thank you.
Okay, thank you, Devwala.
Yes,
it was a nice talk. Any question? Okay, now I hope there is no question.
But there is a comment that
yes,
this comment is for Ramakrishna Patra. So you can see the chat room that Devdutt has asked for reference of your work.
okay. Yes, comment of Devdutt to Ramakrishna Patra.
So any other questions for any speaker of the session? Not only the last speaker, if anyone wants to speak, ask any questions to any other speaker also. If not, let us thank the speaker and also both the session chairs, Dr. Amit Verma and Dr. Sandeep Mishra. And of course, the participants were here. In some places it's odd time, still people are listening so many talks, and it was wonderful.
Can we take a group photograph?
Yes, that will be nice. So all those who has camera, please, it will be nice if you can switch on, at least who are comfortable with that, and then we can take a group photo.
Sandeep, Dr. Sandeep, you may take the group photograph, please.
And we would also like to thank those who are in YouTube. So there are several people, because the room was full, they were in YouTube. And thanks everyone for joining.